Hi everyone, welcome to goclasses. In this lecture, we will study recursive descent parser with backtracking. This is one type of top-down parser, that is recursive descent parser. So let's study. In the previous lecture, we have seen types of top-down parsers. So there are two type of top-down parsers. One is with backtracking, another is without backtracking. You can see without backtracking, it is also called predictive parser because it will use a parsing table. Okay, there is a predictive parsing table, and with the help of that table, it will make its decision like which production to choose. That decision will be made based on the parsing table. Okay, yes or no? So you can see in the previous lecture we were discussing this top down parsing. This is one of the parsing approach. One is top down parsing, another is bottom up parsing. So you can see in the top down parsing what we do, we start from the top, means we start from the start variable and we apply the productions until we arrive at the desired string. So basically in this top down parsing, we start from the start variable and then we apply the productions. Okay, let's assume here you have this non-terminal a, then again we apply the productions. Okay, so like this we keep applying the productions until at the end we want our input string. Okay, input string w. So you can see this is the top down approach. Okay, we start from the start variable and we go from top to bottom, from top to down to the input string. Okay, very simple. Now you can see in this top down approach, what is the challenge? The challenge is choosing this production, like which production to apply. For example, here you can see this is the non-terminal s, so which production of s should I apply? Similarly, this is the non-terminal a, so which production of a should I apply? So that is the challenge we face in the top down parsing. Okay, now you can see there is something called ll1 parser, which is predictive parser, or I can say this is a top down parser without backtracking. So what this ll1 parser will do, this will use a parsing table, ll1 parsing table, or you can say predictive parsing table. So with the help of that parsing table, it will decide, it will choose which production to use. Okay, at any step for any non-terminal, which which production to use, that will be decided based on this parsing table, this predictive parsing table. Okay, very simple. So that is called without backtracking top down parser, or I can say predictive top down parser, because here we are predicting. Okay, there is a prediction based on this table. Okay, based on this ll1 table, we are predicting like which production to choose. Okay, very simple. Now you can see, so in this approach there is no backtracking, we don't need any backtracking. This is also called ll1 parser. Okay, or you can call it predictive parser. So this we have already seen in the previous lecture. In this lecture we need to study another top down approach, that is with backtracking. It is also called brute force, it is also called recursive descent parser. Okay, so you can see that this is top down parsing with backtracking. You can also call it brute force top down parsing. You can also call it recursive descent parser with backtracking. Okay, very simple. So let's see what we do in this approach. In this approach, you can see this is basically brute force approach. Okay, so in this approach we use backtracking. Okay, what it means, it means that there is no table, we do not have any parsing table. So in this approach, in this brute force approach, or I can say in this recursive descent parsing approach, what we do, how do you choose this production? Because this is a top down parser, this recursive descent parser, this is a top down parser. So you can see at any step for this non terminal a, which production should I choose? There is no table to tell us. Okay, in the ll1 parser we have a table that will tell us, but in the recursive descent parser there is no table that will tell us like which production should we use. So what this recursive descent parser will do, it will apply brute force approach. What it means, it means that for this a, let's assume you have multiple productions, alpha 1, alpha 2, alpha 3. Let's assume these are the three a productions. Okay, for this non terminal a, let's assume these are the three productions. Then what this recursive descent parser will do, it will hit and trial. Okay, it will use hit and trial. So basically it will first try this. Okay, this production it will try. If it is successful, if this production is successful, then it will never try these. Okay, but remember, if this production is not successful, then it will try this production. If this production is successful, then it will never try this production. So you can see, but if this production is also not successful, then it will try this production. Okay, so this production. Now you can see, if this production is successful, then very good. But if this production is not successful, then we will say that there is a failure. Okay, very simple. I hope you understood. So remember, in the recursive descent parser, this is what we do. We apply the brute force approach. Okay, basically we do hit and trial. Okay, we just try all these productions one by one. If some production is successful, then we will not try the remaining productions. Okay, but if these productions are unsuccessful, then we will try the next production. Okay, we will backtrack and we will try the next production. This is your recursive descent approach. Very simple to understand. Okay, so you can see here, recursive descent parser is also called brute force parser. It is also called top down parser with backtracking. It basically generates the parse tree by using brute force and backtracking. Very simple. Okay, I hope you understood. So remember, in the gate exam, they can tell you top down parser with backtracking. So that is also recursive descent parser. They can tell you top down parser with brute force. That is also recursive descent parser. Or they can tell you recursive descent parser, or they can tell you recursive descent parser with backtracking. So basically, these are the words they can use. Okay. And I told you what is the idea. The idea is very simple. The idea is basically brute force. Okay, very simple. Now let's see, how does this recursive descent parsing work? Okay, recursive descent parser with backtracking, how does it work? So the idea is very simple, basically hit and trial, or I can say brute force. So let me tell you what we do. We start with the start variable. Remember, it is a top down parser, so we will always start with the start variable. So very simple, that this is the starting point. Okay, we will start with the start variable. We will start, so this is our starting point. Very simple. Now you can see, for this start variable, let's assume for this start variable we have some productions. For example, let's assume this is the production xyz, then there is some other production alpha 1, there is some other production alpha 2, like this. Okay, now remember one thing, that what this recursive descent parser will do, it will try these productions one by one. Okay, but remember, it will it will not randomly take these productions. Okay, it will take these productions in a specific order. Okay, that is important to understand, that this recursive descent parser, it will apply hit and trial, but in a systematic way. Okay, it is a brute force approach, but in a systematic way. Means, you can see here, for this non-terminal A, we need to try one of these productions. But which productions should I try? So remember, these productions will be tried, will be applied in this order. Okay, in a particular order. So by default, we will follow this order. And in the gate exam, or in the question, if they tell you that, okay, if they give you some specific order, for example, first you try this production, then you try this production, then you try this production, if they tell you some specific order, if they tell you, then you need to follow that order. Okay, but by default, if we are writing in this order, then we will apply them in this order by default. Okay, so remember, here I am saying that this recursive descent parser, it will it will do hit and trial, it will try these productions, but remember, not randomly. Okay, it's not like randomly it will try any random production. No, it will try these productions in this specific order, in this fixed order. Okay, very simple. So you can see here, this is a non-terminal. So for this non-terminal, first we will try this production. Very simple. Okay, so first we will try this production x, y, z. Very simple. Okay, now notice, this x can be either a terminal or it can be a non-terminal. Okay, so here let's assume that our input string, so let me also write here, let's assume our input string, let's assume on our input string, the current symbol, that is a. Okay, let's assume like this, and at the end there is dollar, yes or no. So this dollar is a special symbol that will indicate end of the string, end of the input string. So let's assume this is the current symbol on the input string. Okay, means we are here, let's assume this is the current symbol. Now you can see, we have applied this production we are trying. Okay, we are trying this production. So you can see, if this x is equal to a, then what? You can see, if this x is equal to a, then what? Then in that case, this x is successful, because x is equal to a, so this x is successful. We will go to y, and on this input string we will go to next symbol. Okay, so very simple point here, what I am saying, this is the case number 1. Case number 1, that is, if this x is equal to a, if this x is equal to a, then then what we will do, then this x is successful. Okay, we will put a tick mark here. Then I can say, you can see this x is successful. Okay, then I will say that this x is successful. Okay, x is successful. I will put a tick mark here. On this x I will put a tick mark. Okay, means basically you tick x. Okay, you tick this x. And also what you do, you go to y. Okay, because this x is successful, so now we will go to this y, we will go to, and also on this input string we will go to next symbol. Okay, so you can see, move to next symbol, move to next symbol on input string. Okay, very simple. I hope you understood this point. Okay, very very simple point. Let me tell you one more thing here. Okay, before we consider the remaining cases. Okay, so let me tell you one more thing. This I told you in the previous lecture also, so let me repeat this point, that the top down parser, what it will do, it will read the input from left to right one symbol at a time. Okay, so remember, whatever top down parser you take, whether you take with backtracking or without backtracking, means whether you take recursive descent parser or ll1 parser, whatever top down parser you take, remember, we will scan the input string we will scan from left to right one symbol at a time. That is one point. The second point, whatever top down parser you take, recursive descent parser or ll1 parser, whatever top down parser you take, remember, top down parser will always produce leftmost derivation. Okay, so you can see this top down parsing, this can be viewed as finding leftmost derivation for the input string. Okay, so remember, whatever top down parser you take, recursive descent parser or ll1 parser, the top down parser will produce the leftmost derivation. Basically, the top down parser will be finding the leftmost derivation for the input string. Okay, very simple. Now, so let's come back to our example. So you can see this case number 1 we have seen here. If this x is equal to this a, okay, this x is equal to the current input symbol, then in that case this x is successful. We will put a tick mark on x, we will go to y, and on the input string we will move to the next symbol. Okay, very simple. So this is the case number 1. Now let's see the case number 2. What can be the case number 2? What do you think? Case number 2. The case number 2 is if x is a terminal but not equal to a. The case number 2 is if x is a terminal. Okay, x is a terminal symbol. If x is a terminal but x is not equal to a. Okay, in this case, what will happen? Use your intuition. What should happen? This x, this is a terminal. For example, this can be b. So this is not equal to a. So in that case, what will happen? Then I will say this x has failed. Okay, yes or no? Then I will say x is unsuccessful. Okay, x is unsuccessful. And remember, when I say this x is unsuccessful, like cross it. Okay, if I cross it, then if this x is unsuccessful, it means this whole production is unsuccessful. Okay, so remember, this x is unsuccessful, so it means this production s going to xyz, that is also failed. Okay, that is also failed, that is also unsuccessful. So what we will do, tell me what we will do. Try next as production. Okay, yes or no? We will try the next as production. Okay, then this next as production we will try, we will backtrack. Okay, so basically here I can say so backtrack. Okay, you backtrack. Okay, basically go back to s. Okay, you can see, you remove this, go back to s, and you try next as production. So you can see, just do backtrack. Okay, and then you try next as production. I hope you understood. Very simple. Okay, very common sense kind of thing. Okay, this algorithm. Now let's see what is the case number 3. The case number 3 is if x is non-terminal, then what? The case number 3, that is if x is a non-terminal. If x is a non-terminal, then let me tell you, you don't even have to look at the input string. Blindly try one of the x production. Okay, so you can see, if x is a non-terminal, then blindly What I mean by blindly? Blindly means don't even look at the input string, don't even look at the current symbol, okay, current input symbol. Blindly, what you do, try a X production. Okay. And remember, how do I try the X productions? Maybe X has many productions. Then how do we try these X productions? For example, let's assume this X has many productions. For example, beta 1, beta 2, okay, like this, beta 3. Then remember, I told you that don't randomly choose a production. Okay, we will choose productions, but in a specific order. First, we will try this beta 1. If it is successful, we will never try beta 2, beta 3. But if this beta 1 is not successful, then we will try beta 2. If beta 2 is successful, we will never try beta 3. But if beta 2 and beta 1, if these are unsuccessful, then we will try beta 3. Okay, so basically, try an X production. Okay, that's it. Very simple. So these are the cases. Only these three cases are possible, nothing else. Okay, so the algorithm, what is that? You can see the idea. Basically, there are two cases. Okay, case number one, that is if X is terminal. Okay, if X is a terminal, then what to do? These are the two cases. If X is a terminal, then what to do? And case number two, if X is a non-terminal, then what to do? Okay, you can see if X is a terminal, then there are two possibilities. You can see if X is equal to A and if X is not equal to A. Okay, if X is equal to A, if X is not equal to A. You already know if X is equal to A, success. Okay, success means this X will be successful. Tick X. Basically, what we will do, we will tick X. Okay, and then what we will do, we will go to Y. Okay, then what we will do, we will go to Y basically. Okay, you already know we will go to Y and we will go to next symbol on the input string. But remember, if X is not equal to A, this is a terminal. For example, this can be B, small b, and that is not equal to A. Then in that case, there is a, this production has failed. Okay, it means that, means it simply means that this S going to XYZ, this is unsuccessful. Okay, or and what it means? It means try the next S production. Okay, very simple. And you can see if X is non-terminal, then what to do? Then blindly, then in this case, what you will do? Blindly try an X production. That's it. This is the algorithm. I hope you understood. Okay. So you can see everything that I told you that is written here. So let's just quickly read this. You can see recursive descent parser with backtracking. How does it work? It uses hit and trial, or I can say brute force approach. You can see we will begin with the start variable S. Okay, we will start from the start variable S because this is a top down parser. So we will start from the start variable. Okay, you can see. Then we will apply S productions one by one in a fixed order. The order is fixed, the order is pre-decided. Okay, so remember, we will try the productions one by one, but not in a random order. Okay, we will try them in a fixed order, that is pre-decided order. Very simple. Then what you will, then what are the next step? Assume we apply, means assume we are trying this production as going to XYZ. And let's assume on the input string, the current symbol, the current token, that is A. So these are the cases. If X is equal to A, then you move to the next symbol, move to the next input symbol, go to Y. Okay, means this X is a success. Tick X. Okay, you can tick mark X. Then you can see if X is a terminal different from A, then this production is unsuccessful. So you will try next as production. If X is a non-terminal, then blindly, what it means? When I say blindly, it means without looking at the current input symbol. When you see a non-terminal, then blindly apply X productions again one by one in a fixed order. Okay, very simple. Now let's see the final steps. Okay, the final steps are like this. You can see at any step for any non-terminal n, if some production is successful, then we will never try the next production. This I told you, yes or no? Okay, for any non-terminal n, at any step, if some production is a success, local success, okay, we are not looking for the global success. What is a global success? When I say global success means the original input string you have passed. Yes or no? You have derived the original input string. That is called global success. Okay, you have original input string and that you have derived. That is called global success. But I am talking about local success here. You can see at any step for any non-terminal n. If some production is locally successful, if some production is successful, then n will never try the next production. Very simple. Now let's see the next thing. That is, when can I say parsing will be successful? This is important. Read this. When can I say parsing will be successful? So parsing actually will be successful if the first as we will start with the start variable, yes or no, then we will go, then we will go, then we will go, then we will go like this. So remember, the parsing will be successful if this first, if this starting as, if this is a success, means if you here, if you put a tick mark that okay, this starting variable as, if this is a success, and also, and there is and also, and the input string has ended, means the current input symbol is dollar. Okay, so these are two conditions. Please understand. Here, there are two conditions. The first condition is that the starting as variable from where we have started, okay, the starting as variable, that should be successful. That is one thing. And also, the input string must be consumed, means the input string must be ended, means your current input symbol, that must be dollar. Okay, so then we will say that parsing is successful. So you can read this here, that we say parsing is successful if and only if the starting as variable is a successful and the current input symbol is dollar. Current input symbol is dollar. What it means? It means that entire input string you have consumed. Okay, very simple. Now let's see this note here. Note that at any step for any non-terminal n, only its local success matters to it. Remember, at any point of time, for example, you will start from the start variable. Okay, then you are going like this. Then let's assume this is n. Now remember, for this n, for this non-terminal n, only its local success matters. Is this production that it is applying, is this successful? If this is successful, then this n does not care about the global success, like the original input string, whether that will be derived or not, it does not care. Okay, you can see, if its production is successful, then it will never try the next production. Never, never, never. You can see, let's assume n is going to alpha 1, alpha 2, alpha 3 like this. And let's assume that for this n, let's assume this alpha 2 production is successful. Alpha 1 is unsuccessful, this is unsuccessful, and let's assume alpha 2 is successful. Then this n will never try this alpha 3. Okay, very simple. So basically, this n only cares about its local success. This n will say that my production is successful, my alpha 2 production is successful, so I will never try the remaining productions. Very simple. Okay, so you can see, at any step for any non-terminal n, only its local success matters to it, not the global success for the for the entire input string. Okay, so that's it. This is the theory. I hope you understood the theory. It was very intuitive. Do you agree? The working of recursive descent parser, did you understand? Very intuitive working. Okay, now we are going to take a lot of questions, also standard questions from the Ullman book. Those also we are going to solve. Okay, and you will find that this recursive descent parser, this is a very easy topic and very interesting topic. Some very interesting questions can be created on this recursive descent parser. Okay, so everything that we have seen, I hope you understood. Now let's go back to examples. Okay, so let's start practice. A lot of practice we are going to do. So you can see recursive descent parser with backtracking. Consider the grammar. This is our grammar and input string, that is CAD. Okay, so let's see how the recursive descent parser with backtracking will parse this string. Okay, so let's see here. You can see our string is what? Our string W, that is equal to CAD. Okay, initially you can see this is our current input symbol. This is the initial situation, and initially we will start from the start variable. Okay, very simple. Now you notice one thing. This is a non-terminal, yes or no? And I told you, whenever you see a non-terminal, what you will do? Don't even look at this. Don't look at this input string without looking at this input string, because this is non-terminal. So blindly try one of its production. Okay, you can see. So there is only one production for S. So we will apply this production. So S going to C A D. Okay. Now notice one thing. This C, does it match with this C? Are they matching? Yes, they are matching. So you tick it. Okay, you put a tick mark here that okay, this C is successful. Okay, this C is successful. Okay, because they are matching, you can see this C comma C, they are matching. So you put a tick mark here that this is successful. Now you go here, and on the input where you will go, on the input where you will go, now you will go here. Okay, you can see on the input string, you will go to the next symbol. Now notice one more thing. This is the non-terminal. So what should I do? Because this is the non-terminal, don't look at the input string. Don't look at the current symbol. Don't look at the current input symbol, because this is non-terminal. So apply its production. And remember, when we apply a productions, then we will not randomly apply. We will apply them in a fixed order. In this fixed order, we will apply, right? Correct? Yes or no? In this fixed order, we will apply these productions. So you can see, I will apply A going to AB. Okay, this production I will apply. Is this clear? Very simple. Now you can notice this A and A, are they matching? Yes, they are matching. This is the current input symbol, this A and this A. Are they matching? Yes, they are matching. So you put a tick mark here. Okay, a tick mark that okay, this is also successful. This A is also successful. Okay, now you can see, because A and A, because they were matching. So what I will do, tell me, on the input, I will go to next symbol. Okay, and also now here I will go B. Now you tell me, this B and this D, are they matching or not? No, they are not matching. Yes or no? You can see this is a terminal, and this B comma D, they are not matching. So you put a cross here that this is unsuccessful. This B is unsuccessful. You put a cross here. Okay, and remember this cross, what it means? It means unsuccessful. Okay, and when I put this tick, what it means? It means successful. So tell me, here you can notice, because this is unsuccessful, what it means? It means this production is unsuccessful. Okay, this production that we tried for A, that production is unsuccessful. So now what you will do, tell me, you will backtrack to A and you will try the next A production. Yes or no? Is this point clear? So remember, here you can notice, okay, because of this I can say that this A going to AB, this production unsuccessful. This production failed. Okay, this production failed, please understand. Only this production failed. So we will try the next A production. Okay, we will backtrack. Okay, now you can see we will remove this, and on the input also we will backtrack. On the input also we will backtrack basically. Now we will go here and we will try the next A production. So you can see, now remember what you will do. S going to CAD. Okay, and remember already this C was successful, and you can see this W. On this input also you will backtrack. Okay, so where I will go, already this C and C, they are matching. Okay, you can see this C and C already they are matching. So basically now this is our current input symbol. Okay, you can see that we are doing the backtrack. In the past tree also we are doing the backtrack, because this production is unsuccessful. So we will go back. Okay, we will remove this, we will go back to this A, and for this A we will try the next production. Okay, you can see we will try the next production. And notice on the input string also we will backtrack, because only C is matching with C. So now our current input symbol, that is A. Okay, now notice one thing. Now you can see the current input symbol, that is A, and this is also A. So they are matching. So this is success. Yes or no? This A matching with current input symbol. So this A is success. And you can see, because this A is success, it means this A is also success, because this A is going to A. Okay, basically from this A point of view, it is just going to A, and that is success. So automatically this A is also success. Okay, and remember, because this A was matching with this A, so remember now our input symbol is D. Okay, current input symbol, now that is D. Okay, now you can notice this A has become successful. This A has become successful. Now let's see whether this D will become successful or not. You can see this D is matching with the current input symbol. Okay, the current input symbol is D. So D is matching with the current input symbol. So this D is also successful. Now notice from this S point of view, all its branches are successful. Yes or no? From this S point of view, all its branches are successful. So this S will say that, okay, I am also successful. Very good. This S will say, I am also successful because all my branches are successful. So I am also successful. Okay. Now notice one more thing. You notice here that this D was matching with D. Yes or no? So when D is matching with D, so on the input we will move to the next symbol, and the next symbol is dollar. Okay, because you can see when D is matching with D, so we will move to the next input symbol, that is dollar. So you can notice here what is happening at the end. What is happening, that this starting S has become successful, and we are at dollar. Okay, the current input symbol, that is dollar. So overall what I can say parsing successful. Okay, yes or no? Overall I can say parsing successful. Why parsing is successful? Parsing is successful because the reason is very simple, because at the end you can see that starting as is successful, starting as variable successful, starting as variable is successful, and we are at dollar, and we are at dollar. Okay, so I can say and and we at dollar. Okay, I can say like this. So we at dollar. That's it. Okay, I hope you understood this. So this example, did you understand? Very simple. I hope you understood this. Okay, so just put a tick mark. If something is successful, just put a tick mark. And if all the branches are successful, then this variable also you put a tick mark that all that okay, this is also successful. And remember, whenever there is a matching, then you move to the next input symbol. Okay, so these basic things you have to do. Basically, if something is successful, for example, let's assume you have something like V. If all its branches are successful, then this V also will become successful. And remember, whenever some terminal is matching, for example, if this terminal is matching with the current input symbol, if they are matching, then in that case you move to the next input symbol. Okay, very simple. These basic things you have to do. That is your recursive descent parser. Okay, so you can see in these diagrams, you can easily understand that we will start with the variable S. We will try this production. There is only one production, so we will try this production. You can see C is matching with this C, so I can say this C is successful. Okay, now this A is the current input symbol, but you can notice that this is the non-terminal. So blindly we will try these productions in this order. So we will first try A going to AB. That is not successful. Okay, you can easily see. Okay, you can see C, A, then this B and this D, they are basically not matching. So basically this production is unsuccessful. So we will try the next production, and now that is successful. Okay, then you can see all these branches are successful. This S is successful. Okay, and at the end we are at the dollar. Okay, so basically the explanation we have already seen. You can see this diagram. I hope you understood. So read this. This is the working of recursive descent parser. You can see recursive descent parser with backtracking. You can read this here. In this recursive descent parser, what we do, at every step there can be many choices of production to use. Yes or no? For any variable, for any non-terminal, at any step there can be many choices of production to use. So what we will do, we will apply the productions one by one in a fixed order. And remember, we will backtrack if if our choices are bad, or I can say if our production that we applied, if that is unsuccessful, then we will backtrack and we will try the next production. Okay, so basically we will do the backtracking to undo the bad choices. Okay, very simple. So you can read this here, that one solution to top down parsing would be to implement backtracking. And you can see, based on the information the parser currently has about the input, based on the input, basically based on the input string, what we do, a decision is made to go with a particular production. If this choice leads to a dead end, the production that you apply, if that leads to a dead end, then parser will have to backtrack to that decision point. Okay, to that decision point, the parser will have to backtrack. Also, on the input string also we have to move backward. Okay, on the input string also we have to backtrack. Okay, then you can see we will start again by making a different choice, a different production we will try, and so on, until either we have found a successful production, then it is very good. Okay, or we run out of the choices. If we run out of the choices, then it means that I can say that non-terminal has failed, basically. Okay, yes or no? If we run out of the choices, it means that non-terminal has failed. Okay, so please understand here that for any non-terminal n, you will start from the start variable. Okay, you are doing like this, you are doing like this, you are doing like this. Now, let's assume this is the non-terminal. For this non-terminal, if all the productions that I apply, if they are unsuccessful, let's assume first you apply alpha 1, that is unsuccessful, alpha 2, that is failed, alpha 3, that also failed. Then what you will say? Then you will say that this n is unsuccessful. Then you will say this non-terminal is failed. If this non-terminal failed, what it means? It means that this branch has failed. So whatever non-terminal you have here, for this non-terminal, you will try a new production. Okay, for this non-terminal, you will try a new production. Okay, very simple. I hope you understood. Let's consider this grammar and let's try to parse this input BCD with recursive descent parser with backtracking. Okay, so let's see here how the recursive descent parser will try to parse this input string BCD. So you can see our input string W, that is equal to BCD, and there is a dollar, okay, to indicate the end of the string. So there is a dollar. Now you can see this is our current input symbol. Initially, this is the current input symbol, because I told you that whatever top-down parser you take, the input string, we will always scan from left to right one symbol at a time. So you can see initially, this is the current input symbol. Okay. And we will start from where? We will start from the start variable. Very good. Now you can see, because this is a non-terminal, I told you that the recursive descent parser, whenever it has a non-terminal, then without looking at the input string, without looking at the current input symbol, what we will do, we will try one of as production. But when we try the as productions, we will not randomly choose a production. Okay, we will choose the productions in a specific order. So you can see these productions I will apply in this specific order, and these productions I will apply in this specific order. So you can see first we will apply BAB. Okay, first we will apply BAB. This is what I will apply. Now notice one thing, B and B matching or not? Yes, matching. So this B is successful. This particular B, let's put a tick mark that okay, this is successful. Tick mark means that this B is successful. This B is successful. Okay, this is what this tick mark means. Very simple. Now you can see when B and B, when they are matching, so what I will do, now I will go to the next symbol. Okay, on the input I will go to the next symbol. Now you can see this is also terminal, this is terminal. Okay, you can see this C comma A, they are not matching. What it means, C comma A, they are not matching. What it means, it means that this has failed, this A has failed. So what it means, it means that this production has failed. Okay, please understand, it simply means that this production failed. I can say here I can say that S going to BAB failed. Okay, no problem, no problem. If S going to BAB failed, now we will backtrack, we will remove this. Okay, our bad choices we will undo. Okay, in the real life we cannot do that, but in the parser, in the recursive descent parser, we can do this. Our bad choices we can undo, and then we will backtrack, we will go to S. Now this S, what it will do, it will try the next production, no problem. So you can see that we will backtrack. Okay, now notice, now this S will try the next production. But notice one more thing, on this input also you will backtrack, because we have already removed this production, we have already removed our bad choices, we are backtracking. Now we are here, so I can say that on the input also we will go backward. Okay, so you can see now basically we are here. We are on the square one, I can say. Okay, because basically there is no progress. Now again you can see this is the current input symbol. Yes or no? Because basically we are at the initial situation again almost. Okay, you can see. So this production we have already applied and this production has failed. So let's try the next production. So you can see this S will try next production BA. Okay, now you can notice this B and this B, are they matching or not? Yes, they are matching. So this is a tick mark. This is a small success we got. Okay, so because this B and B, because they are matching, so I will go to next symbol on the input string. Okay, now my current input symbol, that is C. So you can see here, now you notice this is a non-terminal. When you see a non-terminal, then the recursive descent parser will try a production without looking at the input string, without looking at the current input symbol. Blindly we will try a production. And remember, the a productions also we will try in this fixed order. In this fixed order, basically I will try this D first. Okay, very good. Now you can see this D, is it matching with C? Because remember, current input symbol, that is C. So this D, is it matching with C? Again there is a failure. Okay, yes or no? So what it means? It means that here I can say that this A going to D failed. Okay, now remember, when A going to D failed, so this bad choice I will backtrack, I will undo this bad choice, I will basically go to A and I will try the next A production. Yes or no? So you can see that basically now you are here, that okay, B C D dollar. Okay, and basically this S going to B A. Okay, next you can see this B is already a successful. Okay, this B was already a success. And you can see now you are here. What it means? It means that the current input symbol, that is C, because already remember this B was a success. Okay, this B was already matching. So you can see basically this is the current input symbol. And now you are standing here and you will try the next A production. Okay, the next A production you will try. Very simple. Now you can see this C, is it matching the current input symbol? Yes, they are matching. C and C, they are matching. So just put a small tick mark that okay, we got a small success, small local success we got. Yes or no? So put a tick mark that we got small local success. Very good. Now this is the non-terminal. For a non-terminal, what we will do? I told you the recursive descent parser, whenever it will see a non-terminal, it will try one of, it will apply one of production. Okay, in this specific order. So for this non-terminal, we will try these productions, we will apply these productions in this specific order. So we will first try A going to D. Okay, one more thing you remember, when this C was matching with this C, so now on the input we are at D. Okay, because this C was matching with this C, so on the input string we will move to the next symbol, that is now the current input symbol, that is D. D is matching with D or not? Yes, D is matching with D. So you put a small tick mark here that okay, we got a small local success. Small local success we got. Let's celebrate. Okay, so you can see from this A point of view, all the branches are successful. Only one branch is there that is successful. So basically, from this A point of view, I can say this production has become a success. So this A also you tick mark that okay, this A has become success. Means this production has become success. Now notice from this A point of view, from this A point of view, all the branches are successful. Yes or no? This A is saying, this A will say that okay, all my branches are successful. You can see this branch and this branch both are successful. So I am also successful. Okay. Then you can see what this S will say. This S will say, my both branches are successful. Okay. Both my kids are successful. So I am also successful. Okay. Now notice this S has become successful. And now where are you? Remember, when this D was matching with this D, then we will move to the next symbol on the input, yes or no? Because already this D was matching with this D. So on the input, we will move to the next symbol. So now we are at dollar. You are at the dollar also. This starting S has become a success. Okay, so finally, what the final thing I can say? Finally, finally, I can say that this starting S from where everything started. Okay, basically, this starting S from where everything started. This starting S is a success. Okay, and also remember, on the input you are at dollar. on the input we are at dollar. Okay, so I can say successful parsing. Okay, so you can see here I can say successful parsing. Very simple. I hope you understood this recursive descent parser. Okay, so basically everything that we have seen that is written here, if you want to revise, then you can read this. You can see dead end, backtrack. Okay, everything that we have seen that is written here. So you can notice in our previous example, two examples we have seen. In both examples, you can see, as you can see, each time we hit a dead end, we backtrack. Okay, we back up to the last decision point. We unmake that decision. Okay, we undo our bad decisions. Then you can see we unmake that decision and try another alternative. If all the alternatives have been exhausted, then we back up to the preceding deciding point. Basically, we backtrack to the preceding decision point and so on. This continues until we either find a working pass tree or we have exhausted all the combinations without success. Okay, very simple. We are going to take many more examples, many more questions, but I hope you understood the working of recursive descent parser. So you can see this was the working of recursive descent parser that we have seen. Recursive descent parser with backtracking. How does it work? With help of hit and trial. Okay, or I can say brute force approach. I told you it will begin with the start variable s. We will apply s productions one by one in a fixed order, a pre-decided order. And remember, assume we apply this production s going to xyz, and let's assume that the current input symbol is a. Then there are three cases. What are the three cases? If x is equal to a, then we will move to the next input symbol and we will go to this y. Okay, basically this x has become a local success. You can tick this x. If x is a terminal symbol different from a, then it means this production has failed. So we will try the next s production. If this x is a non-terminal, then blindly, without looking at the current input symbol, without looking at the input string, blindly apply x production again one by one in a fixed order. Okay, also I told you at the end what will happen. You can see at any step for any non-terminal n, if some production is local success, then n will never try next production. And remember, when can I say parsing is successful? Parsing will be successful if and only if the starting variable s, that is a success, and the current input symbol at the end, that is a dollar. Okay, very simple. Let's consider this example also. So here this grammar is given to us, and the token stream means the input string that is given to us. Okay, forget about this 5. Okay, forget about it. So you can see this token stream is, this input string is given to us. So we need to apply the recursive descent parsing. We will start with the top level non-terminal e. You can see here, this is the start variable. This e is the start variable. So remember, we will start with the top level non-terminal e. And because this is a non-terminal, so what the recursive descent parser will do, it will try the rules for e in order. Okay, focus on this word, in order. Basically, in this order we will try the productions. Okay, in this order we will try the productions. In this order we will try the productions. Very simple. Okay, so let's see what will happen here. Let me write the grammar here. Okay, e going to t or t plus e. Okay, and you can see t going to int or int star t or parenthesis e close parenthesis. Okay, very simple. So you can see this is the grammar, and what is our input? What is the input string w? That is this. Okay, so let's see how the recursive descent parser will do its parsing. So you can see w is equal to what? The input string, that is left parenthesis int right parenthesis. Okay, remember one thing here, this int, this itself is a token means this itself is a input symbol. It's not int, it's the whole. It's basically there are three symbols. You can understand like this. Okay, is this clear? One, two, three. Okay, because remember, basically these are tokens. This is a token. Notice one thing. This is a token, left parenthesis token, int integer token, then this right parenthesis, this is a token. So basically in this input string, if I ask you what is the length of this input string, that is basically here 3. Okay, so this itself is a token. Okay, what this I when I say length is 3, it means basically 3 tokens. Okay, now anyway, so let's see what the recursive descent parser will do. It will start from the start variable. Let me start from the start variable. Now because this start variable itself is e, yes or no? Start variable is e. So you can see, let me start from the start variable, that is e. Now because this is non-terminal, so what we will do, without looking at the input string, we will try these e productions in this order. Okay, so you can see first we will try this production. Okay, e going to t. Now you can see this t itself is a non-terminal. For a non-terminal, what we will do, without looking at the input string, we will try these t productions. First we will try this production. Okay, so you can see like this. Now you can see this is a terminal. Is this terminal? Remember the current input symbol, that is left parenthesis. On the input, the current input symbol, that is left parenthesis, and this is the terminal. Is this terminal matching with this terminal? Are they matching? Let's see, are they matching? No, they are not matching. Mismatch. Okay, yes or no? There is a mismatch. You can see there is a mismatch. So because there is a mismatch, so what it means? It means this has failed. Okay, when I say this has failed, it simply means this production has failed. Okay, notice one thing here. I can say that here, I can say that this t going to int, this production failed. This production failed. So when this production failed, it means you will remove this. Okay, you will backtrack, you will go here and you will try the next t production. Okay, very simple. So you can see the next thing will be, again let me write the input string, that is int. On the input string, still you have this current input symbol, left parenthesis. So you can see this e will go to t, and now this t will try its next production. Okay, so you can see this t will go to int star t. Again you can notice this int and this left parenthesis, there is again a mismatch. Yes or no? This is a terminal, and again there is a mismatch. Again there is a mismatch. And because there is a mismatch, what it means, okay, you put a cross mark, small cross mark here. What it means? It means that this production has also failed. Okay, yes or no? So remember, I can say that this t going to int star t, production failed. Production failed. Okay, no problem, no problem. If this production failed, then we will try the next t production. Okay, basically we will undo our mistakes, our bad choices, we will undo, we will backtrack, we will go here, and from this t we will try the next production. Okay, so let's see. Remember, still this is the current input symbol. Okay, now you can see basically this is the situation. Now this t will try the next production. Okay, so this t will try the next production. Very simple. Now notice one thing. You can see this. This is a terminal. Yes or no? Is it matching? Yes, they are matching. Very good. If they are matching, you put a small tick mark that okay, we got a local success. Okay, a small success you can celebrate, basically that we got a local success. Okay, and now because they are matching here, this and this, because they are matching, so on the input you will go to the next symbol. Okay, on the input string you will move to the next symbol. Now notice here what you have, this e. What is this e? This is a non-terminal, and whenever recursive descent parser will see a non-terminal, without looking at the input string, without looking at the current input symbol, it will try e productions in a specific order. Okay, so you can see here, for this e, what you will do, you will try a production. Okay, so this e going to t, this production you will try. Clear? This you will try. Then you can see again this is a non-terminal. This t itself is a non-terminal. So again we will try T productions. In this specific order, we will try T productions. So you can see this T will go where? This T will go to int. Okay. So let me write on basically here. Let me write that now. What are the next thing? Next. The next thing is basically that you can see this E was going to T was going to this and this and this. Now you can see this E, because this is non-terminal, so we will apply E production. Then this T, because this is non-terminal, so we will apply T production. Okay. Now you can see, already remember, this was already a local success. Okay, this tick mark was already there. Okay. Now you can see this is the current input symbol int. This is also terminal. Are they matching? Yes. Int, this is the current input symbol, and this terminal, they are matching. So here you can put a small tick mark that, okay, I got a small local success I got. Now you can see from this T point of view, all its branches are successful because only there is one branch. So that is successful. So this T will say that, okay, I am also successful. From this E point of view, there is only one branch. Okay. And that is successful. So this E will say, I am also successful. Okay. Now notice one more thing. This int and this int, when they were matching, then on the input also I will move to the next symbol. Yes or no? Because this int, they are matching. So you can see on the input also we will move to the next symbol. Okay. And one more thing, there is a dollar at the end. Okay. Now you can see that here you can notice this E is a successful. This E will say I am a successful. Now you can see the next symbol, that is close parenthesis. This is a terminal. This is a terminal symbol. Is it matching with the current input symbol? Yes, this is matching. So you put a small tick mark here also. Okay, a small tick mark you put here also, that, okay, we got a small success here also. Now notice from this T point of view, one more thing, because this and this, because they are matching. So remember, on the input, you move to the next symbol. On the input, we are moving to the next symbol. So now the current input symbol, that is dollar, because you can see this close parenthesis, this is matching here. Okay. So now the current input symbol, that is dollar. And remember one thing, from this T point of view, all its branches are successful. Okay. So this T will say, I am also successful. I am also successful. Now this E will say that I only have one branch and all my branches are successful. Basically, there is only one branch. So you can see, because this branch is successful, I can say that this E will say that, okay, I am also successful. Okay. Now finally, what I will say, you can see this starting point is successful and the current input symbol is dollar. What it means? So you can see, the starting E is successful. And you can notice that, and current input symbol, that is dollar now. And current input symbol, that is dollar. Okay. So what you will say? So successful parsing. So successful parsing. I hope you understood. Very easy. Okay. So that's it. We have seen. Okay. So basically, this example, you can see this grammar, and for this input, we have seen. Let's solve this Ullman book question. And you can see I've written future gate question. In the future gate, definitely this question or similar question will come in the gate exam in future years. I don't know whether next year or after 5 year, after 10 year, but definitely, because this is a Ullman book question. And remember, Ullman book question, or I can say the standard university question, the standard questions, they come in the gate exam. Okay, that is the reason I've written that in future, maybe someday this type of question can be asked from recursive descent parser. Don't worry, you are now expert. Okay, you can solve all these questions very easily. Okay, all these questions are cakewalk for you. So let's try this question. This is a Ullman book question. Read this question. The grammar S going to AA, ASA. Notice this grammar. Which language will be generated? Even number of A's. Yes or no? I can say this grammar will generate all even length strings of A. For example, A power 2, A power 4, A power 0 will not be generated here. So basically, all non-empty. Here I should write all non-empty. Okay, because empty string will not be generated. Remember, in the empty string also we have even number of a's, because in the empty string we have how many a's we have in the empty string? That is 0. 0 is a even number. Okay, so here I can say that this grammar generates all non-empty strings of even length of a's. Okay, you can see we can devise a recursive descent parser with backtrack, recursive descent parser with backtrack for this grammar. If we choose to expand by production as going to a first, see, read this statement. This is an interesting statement. The question is saying that if we choose to expand by production as going to a first, means this order is given to you that okay, when we apply the productions, when we try the productions for s, then we will apply them, we will try them in this order. Okay, this information is basically this order. This is info about order. Info, this is info about order of productions. That info is given here. Okay, you can see this recursive descent parser recognizes which inputs. Some options are given to you. This recursive descent parser will recognize which inputs. The concept we have already seen. The working of recursive descent parser we have already seen. Okay, we have seen a lot of examples also. We have seen. You are expert. Okay, so let's see what will be the answer. Notice one thing here. This string, they are not even generated by this grammar. So don't even think about them. Okay, you can see. Notice one thing. This string and this string, they are not even in the language of this grammar. So these strings will never be generated. These strings will never be recognized by recursive descent parser or by any parser. Because please understand, these two strings, these are not generated by this grammar, or I can say these two strings are not in the language of this grammar. So whatever parser you take, that will never recognize, that will never generate these strings. Okay, so these strings you can immediately cross mark. Now, notice one thing, that these remaining strings, double a power 4, a power 6, a power 8, these strings are actually generated by this grammar. But now the question is, the recursive descent parser, will this recursive descent parser be able to recognize these strings or not? Okay, the question is this, that these strings, a power 2, a power 4, a power 6, a power 8, these are actually generated by this grammar. But notice, the recursive descent parser, will it be able to recognize these inputs or not? That is the question. I hope you understood the question. Okay, so let's solve this question now. Let me write this grammar. You can see this is the grammar as going to aa or asa. Okay, and you can see the question is saying that we will apply the productions in this order. In this order we will apply the productions. Okay, basically like this. Now let me do one thing. Okay, and notice one thing, that recursive descent parser we have to apply. Recursive descent parsing we have to apply. Okay, so let me do one thing. First let me check this string. First let me check this string small a. Okay, only one a. Okay, basically this option a, let me check. Option a, I told you actually you don't even have to check. What is the reason? What is the reason? You can immediately eliminate option a, option c, because remember, this option a, option c, you notice one thing, that this a does not belong to lg, and this triple a does not belong to lg. Okay, if this is the grammar g, then in this case you can see, in this case these strings will never be recognized by any parser. Okay, so remember, so these will never, these will never be recognized by any parser. Okay, because they are not even generated by the grammar. If they are not even generated by the grammar, then any parser will not be able to recognize them. Okay, so you can just eliminate these two strings, you can immediately eliminate. But anyway, just for sake of practice, I am going to show you how the recursive descent parser will will discard this string, or I can say how the recursive descent parser will say that okay, this string is not recognized. Okay, so let's see how the recursive descent parser will not recognize this string. Okay, so let's see this. So what are the starting point? You can see the starting point is this, that the current input symbol is a and there is dollar here, and you can notice the starting point, that is we will start from the start variable. Because this is a variable, this is a non-terminal, so without looking at the input string, we will try these as productions, we will try in this order. Okay, so first we will try this aa. Okay, now notice one thing, this a is matching with this a. Okay, you can see this a is a terminal and this is matching with the current input symbol, so I can put a tick mark here that okay, this is a small success I got. Okay, a small local success I got, so let me put a tick mark. Then you can see, because this a and this a, because they are matching, so now the next input symbol, that is dollar, that is the next input symbol. But notice one thing, this a is a terminal and a comma dollar, they are not matching, yes or no? There is a mismatch here. Here you can notice there is a mismatch. So because there is a mismatch here, what it means, a small cross mark you can put that okay, this has become unsuccessful. What it means, it means that this production has become unsuccessful. Please understand, here you will say that as going to a production failed, this production failed. Okay, if this production failed, then no problem, we will backtrack. Okay, we will remove this production from here, we will try the next production, and on the input also we will backtrack. Okay, so basically now you are at this position, because you can see this production you will remove. Okay, your bad choices you will undo. Okay, now you are here and you will try the next production, you will try asa. Okay, and remember on the input string also you can notice that on the input string now we are here, because on the input string also we will go backward. Okay, yes or no? So you can see now this is the situation. Now notice one thing, this a and this a, they are matching, so I can put a small tick mark, and you can see on the input string, on the input string I will move to the next symbol. Okay, because you can see this a and this a, they are actually matching, so a small tick mark I can put that okay, this a has become successful. Now I am here as okay, this, notice that this is a non-terminal, so for this non-terminal, without looking at the input string, without looking at the current input symbol, we will try these as productions one by one in this order. So you can see this as, for this as you will try aa. Okay, now notice this a is not matching with this dollar, yes or no? This is a terminal and this is not matching with this dollar, so I can put a cross mark here. What it means, what it tells you, it tells you that this production as going to a production failed. Here I can say as going to a production failed. Okay, and when it failed, then what it means, it means that here you will, you will remove this. Okay, you will go to this s and you will try the next production, yes or no? So you can see that this will happen, that s going to asa, already you can notice that this a was already a success. Okay, and for this s you will try the next production. Okay, and notice that on this w, on this input string, remember you are here because already this a was matching with this a, so basically this is the current input symbol dollar. Okay, now notice this a, is it matching with dollar? This is the current input symbol, this a is not matching, so I can put a cross mark here. What it means, it means that this production also failed. Okay, as going to asa production also failed, this production also failed. What it means, if this production also failed, what it means, now you will remove this production also you will remove, you will go to this s, and now you will ask, do you have any other production to try? This s will say no, I don't have any other production to try, yes or no? Because remember this production has failed, so you will undo your bad choices, you will remove this. Okay, you will backtrack, you will go to this s, you will ask, now do you have any other production to try? Then this s will say no, I don't have any other production to try. So this s will say that okay, I have failed because all my productions has failed, yes or no? This s will say all my productions have failed, so I have failed. Now basically now this production also has failed, yes or no? For this s point of view, from this s point of view, from the first s point of view, this production asa, this production also has failed. Okay, so now you will ask this s, do you have any other production to try? This s will say no, I don't have any other production to try because already this asa production I have tried. So for this s, it will say that I have also failed because all my productions have failed, so I have also failed. Okay, that's it. Okay, so you can see that the starting as has failed. So you can see, so the starting as failed. The starting as failed. And because the starting has failed, so what you will say? Because the starting has failed, so it means parsing failed. Overall, I can say that this string, this small a, this string will not be recognized. Okay, yes or no? This will not be generated, or I can say this will not be recognized. That's it. I hope you understood. So you can see you can eliminate this option A. Similarly, you can eliminate option C without checking. You don't even have to check because remember, these two strings, they are not even in the language of this grammar. They are not even generated by this grammar. So you can just immediately you can eliminate them. But anyway, for just sake of practice, I have showed why recursive descent parser will reject this string. Okay, very simple. Now let's see what about this double a power 4, a power 6. What about these? Now something interesting is coming, and you will appreciate this recursive descent parser. So you can see this string w going to, basically this is the string, okay, a, and of course there is a dollar to indicate that end of input. Okay, so you can see initially this is the current input symbol. Okay, so you can see we will start with the start variable because this is a variable. So we will apply as production in this order. We will apply as production. So we will apply this as going to a. Okay, so you can see that this a, this is matching with this a. So I will put a small tick mark here that I got a small success here, local success I got. But notice because they are matching, so on the input I will go to the next symbol. And you can see this a is also matching with the current input symbol, so I will put a small tick mark here that I got small local success here also. Remember, because this a and this a are matching, so on the input I will go to the next symbol. On the input I will go to next symbol. And now notice one thing, that from this as point of view, all its branches are successful. Basically, from this first as point of view, this production has become successful. So this as will never try this production. Okay, so basically you can see from this s point of view, all its branches are successful. So this s will say that okay, I am also successful because my all branches are successful, so I am also successful. Now notice one thing, that here this starting s is successful, also the current input symbol is dollar. What it means, tell me. So you can see that starting variable s is successful, and and we are at dollar. Okay, yes or no? And we are at dollar. So successful parsing. Okay, so successful parsing. What it means? If successful parsing, what it means? It means that recursive descent parser. Okay, in short, I am writing it RDP. Recursive descent parser recognizes recognizes this string A. Okay, recognizes string A. Very simple. Okay, now something interesting I will show you. What about this string? W going to A. Okay, what about this string? Now, remember this string is actually generated by this grammar, but will this recursive descent parser RDP, will this RDP be able to recognize this string or not? That is the question. Okay, this recursive descent parser, will it be able to parse this string or not? That is the question. Okay, so let's see the ability of recursive descent parser here. So you can see we will start, this is the current input symbol in the beginning, and you can see we will start with the start variable. And remember, the question says that for this non-terminal s, when we apply these productions, then in this order we need to apply. So first we will apply a. Okay, very simple. Now notice one thing, this a is matching with this a, so I will put a small tick mark here that I got a small local success I got. Okay, now you can see because this a and this a, they are matching, so on the input I will go to the next symbol. Now you can see this a, this is also matching with this a. Okay, so here I will put a small tick mark that okay, I got another local success. Okay, now because this A and this A, because they are matching, so now I will go to the next symbol on the input. Now notice one very interesting thing, that from this as point of view, think from this as point of view, this as is thinking that all my branches are successful, so I am also successful. Okay, remember, this as is thinking that this production is successful. And tell me one thing, if this production is successful, if this production is successful, then will we ever try this production or not, the next production? No, we will not try. Yes or no? Because notice, this production itself is successful, so we will never try, the recursive descent parser will never try the next production. So notice that this s has become successful. This s is saying that, the starting s is saying that I am successful. But notice one more thing, because this production has become successful, so we will never try this next production. But notice one thing, that on the string you are not at dollar, or I can say that entire string you did not consume, we are not at dollar. So remember one thing, that this starting as successful. Okay, the starting as is actually successful, that is fine. But we are not at dollar, we are not at dollar. What it means? It means that parsing failed. Okay, yes or no? It means that parsing failed. What it means? Parsing failed. What it means? It means, so recursive descent parser will actually reject this string. Recursive descent parser won't recognize this string for a this string. Okay, is this point clear? Please tell me. I hope this point is clear. And remember, this I told you in this lecture already. I told you that when we will say that parsing is successful, parsing is successful if and only if the starting s variable is successful, and we should be at the dollar symbol, means the current input symbol must be dollar. One more thing I told you, that is, at any step for any non-terminal n, if some production is successful, if some production is a local success, then n will never try the next production. Also, I told you that at any step for any non-terminal n, only its local success matters to it, not the global success for the entire input string. Okay. Now notice what phenomena happened here. If you notice in the previous example, when we were having this string w equal to a dollar, this was our string. Now don't you think that if we start from this production, then we will be able to recognize this? Yes or no? Don't you think? I am saying that if we start from this production, then actually we will be able to recognize this string. But notice, because you are starting with this production and this production has become successful, that is the reason you will never try the next production. And that is the reason we are not able to recognize this string. Even though this string belongs to the language of this grammar, still the recursive descent parser will not be able to parse this string. The recursive descent parser will never be able to recognize this string, because the recursive descent parser is trying these productions in this order. First this production, and when this production becomes successful, it will never go to the next production. Okay, is this clear? In the life also actually this happens. Let me tell you, sometimes in the btech sometimes some students, some very good students, okay, they get, let's assume they get some package. Okay, let's assume 3.5 lp package they get. Okay, in the btech, some, I'm talking about some students who have good potential. Okay, but still what they will do, they will get this, let's assume some package they will get. Okay, in some mass recruiter company, service based company, they will get this package and they will just go for it. Okay, they will take it, they will start the job, and after few years of doing the job, they will actually become very comfortable, and they will get stuck here, I will say. Okay, but actually they have good potential. Okay, instead of taking this job, if they follow their potential, if they recognize their potential, okay, maybe they do something according to their potential. Okay, there are many things. Maybe they prepare for some product based company, Okay, maybe some competitive programming, maybe placement preparation, or maybe gate exam preparation, maybe cat exam preparation, UPSC exam preparation. But the point is that they, because they got a local success, I will say that okay, this first success, basically this first success they got, so they will take it. They will never ever they will never even try what could have been possible. Yes or no? What could have been possible, they will not even know, I will say. Okay, of course they will never have regret. The reason is because they don't even know what they could have achieved. Okay, yes or no? So but I hope that this scenario, this phenomena, I hope you found this phenomena very interesting. Is this clear? Please tell me, let me know. So notice for this question, you can see for this question, this AA, this recursive descent parser will be able to recognize this double A, but recursive descent parser will not be able to recognize 4A, 6A, 8A. Okay, and the reason is very simple. The reason is very simple because first we try this production, and because this production becomes successful, the local success we get. Okay, because this production becomes successful, so we will never try the next production. Okay, you can see the same thing for this string, for example. Let's see the same thing for AA, AA, AA. Okay, for 6A. Okay, so you can see for this string also what will happen. You will, you can see you will start from here. You will scan the input string from left to right, one symbol at a time. So you can see this is the current input symbol initially, and you can see we will start from the start variable. Because this is a variable, so we will try one of as production in this order. So first we will try this production. Now you can see this A, this is matching with this A, so we will go to the next symbol on the input string, and we will put a small tick mark here that okay, we got a local success here. Next you can see this A is matching with this A, so we will go to the next symbol on the input string, and we will put a small tick mark here that we got a small local success here. Now you can see from this S point of view, both its branches are successful, so this S will say I am also successful. So basically from this S point of view, this production has become successful, so this S will never try the next production. Okay, but notice one thing, this S, this starting S is saying I am successful, but notice on the string we are not at dollar, or I can say we did not consume the entire string. So that is the reason parsing failed. Okay, so you can see the parsing actually failed. What is the reason? Because we are not at dollar, because we are not at dollar. Okay, is this clear? So parsing failed. So what we will say, we will say that recursive descent parser will actually reject, will actually reject a power 6. Okay, yes or no? Will reject a power 6. I hope you understood. So this was a very interesting question. This question is a very interesting question from the Ullman book. Okay, many students, they will not be able to solve this question because see, this is a very decent question. There is nothing fancy here. Okay, this is simple question, a simple grammar is given. The question is asking for recursive descent parser, how it will work. Okay, some options are given. So this is actually very simple question. There is nothing fancy here, no fancy concept is here. Okay, recursive descent parser, that is in the gate syllabus. This type of question can come in the future gate exam, but still many students, they will not be able to solve this question. Okay, because they don't learn how the recursive descent parser works. Okay, some some theoretical question they can solve from recursive descent parser. Okay, some true false questions they can solve, but this type of good questions from the Ullman book, they won't be able to solve because they don't really understand how this recursive descent parser with backtrack works. Okay, I hope you understood. Let's solve this question from the Ullman book. This is another very beautiful question based on recursive descent parser with backtrack. So let's solve this question. And now remember, you are expert. The previous question we have seen, in the previous question some things you got to learn. Okay, now this question you can try. I have full confidence on you that you will be able to get correct answer. Okay, so let's solve this question. This is a beautiful question from the Ullman book. Read this question. The question is saying that the grammar S going to ASA or A, this generates all even length strings of A's. Actually, empty string is not generated, so I should say all non-empty. Okay, because empty string is not generated. Remember, in the empty string, how many A's we have? In the empty string, we have there is no A. I can say that number of A, that is 0, and 0 is a even number. So you can see that this grammar actually generates all non-empty even length strings of A's. For example, A power 2, A power 4, A power 6, A power 8, A power 10, like that. You can see we can devise a recursive descent parser with backtrack for the following for this grammar. For this grammar, we can devise a recursive descent parser with backtrack. Now remember, the question is saying that if we choose to expand by this production A first, and this we have already seen in the previous question. Actually, the previous question was actually this, that if we choose to expand by the production S going to A first, S going to A first, if we choose to expand by this production first, then we will not be able to recognize A power 4, A power 6, A power 8. Basically, we will only recognize double A. The other strings we will not be able to recognize. Actually, this statement was your previous question. If you notice, this statement was your previous question that we have done. Before this question, the previous question that we have done, that is actually this statement. So this we have already done. Okay. Basically, in this grammar, if you first expand this production as going to A, if you first expand this production, then only this string we will be able to recognize. Only this string the recursive descent parser will be able to recognize. All the remaining string like A power 4, A power 6, A power 8, all the remaining strings will be rejected by the recursive descent parser. Okay. So you can see the question is saying that any reasonable recursive descent parser, what it will do, it will start with this production. Okay, you can see any reasonable recursive descent parser will try as going to ASA first, means this production it will try first. Now the question is very interesting, that show that if you start with this production, then also we will not be able to recognize A power 6. We will be able to recognize A power 2, A power 4, A power 8 also, but not A power 6. Okay, but not A power 6. This is a very interesting question. Okay, so let's see this. Remember, the working of recursive descent parser with backtrack we have already seen. A lot of practice we have already done. Now you can just take your copy pen. I am doing it, you also do. I have full confidence on you. You can solve this question, this Ullman question, mighty Ullman question, you can solve very easily. Okay, so let me write the grammar here. Grammar G, that is S going to ASA or AA. This is the grammar, and the question is saying that in this order we need to apply the productions. Okay, and remember, we need to parse using recursive descent parser. We need to do the parsing with help of recursive descent parser. In short, we will call it RDP. Okay, so let's see. Let me take the string here, W equal to AA. You can see this string belongs to the language of this grammar, but this recursive descent parser, will it be able to recognize this string or not? That is the question. Okay, so you can see there is a dollar here to indicate the end of the string. So this is the situation. Now you can see any top-down parser will read the input string from left to right, one symbol at a time. So initially this is the current input symbol. Okay, and we will start from the start variable, because any top-down parser will always start from the start variable. So now what this recursive descent parser will do, because this is a non-terminal, so we will try one of as production, and you can see in this order we will try as production. So you can see first we will try as going to ASA. Okay, very simple. Now you can notice that this A and this A, they are matching. So I will put a small tick mark here that I got a small local success here. Okay, that okay, this A and this A are matching. So basically this A is success. And because they are actually matching, so on the input we will go to the next symbol. Now this is the current input symbol A. But remember, here you have non-terminal. So because this is a non-terminal, so what we will do? Again, we will apply as production. In this order, we will apply as production. So you can see that we will apply A as A. This is what we will apply. Now notice, this A, is it matching the current input symbol? Yes, they are matching. So this is a small success I got here. Okay, and because they are matching, so on the input I will go to the next symbol. Okay, now notice again I got a non-terminal. And for this non-terminal, what this recursive descent parser will do, it will try as production. In this order, it will try as production. So it will try as going to ASA. Now notice this A, this is the terminal. Is it matching the current input symbol? No, it is not matching. So this failed. Okay, what it means? Here I can say that this S going to ASA, this production failed. Please understand. Okay, so here I can say that this S going to ASA production failed. Okay, this production failed. Very simple. If this production failed, there is no problem. There is no problem. We will remove this production. We will backtrack. We will go to this S and we will try the next production. Okay, yes or no? So this S will try the next production. This S. Okay, I can mark it here that okay, this S will try the next production. Okay, so you can see this is the situation we got. You can see S is going to ASA. Okay, remember this A was already success. Okay, then you can see this S was going to ASA. Remember this A was already success. Okay, now you can see now we are here. Correct? Okay, because we will backtrack and now we are at this S, and at this S we will try the next production. Okay, the next production we will try. On the input, where are we? On the input, where are we? You can see already 2A are matching, 2A already matched. 2A already matched. So actually we are here. Okay, the current input symbol, that is dollar. Now notice this A. Is it matching this A? It is a terminal. Is it matching dollar? No, it is not matching. So I can put a cross mark here that it got failed. What it means? It means that this production also failed. Notice that this S going to A, this also failed. Okay, what it tells you? Now you will backtrack. Okay, you will remove this production. Now you will go here. Okay, now you will go here, and this S, to this S, you will ask, do you have any other production to try? Because both your productions have failed. We are asking this S. Okay, this S we are asking that both your productions have failed. Do you have any other production to try? It will say, no, I don't have any other production to try. All my productions have failed. All my alternatives have failed. So I have failed. Okay, yes or no? I have failed. Then, because this has failed, so now we will go to this S and we will tell this S that ASA has failed. Okay, to this S we will say that this ASA has failed. So what this S will tell us? This S will tell us that okay, no problem, if ASA has failed, then I will try AA. Okay, is this clear? So notice that now this S will try AA. Okay, is this clear? So basically this S going to ASA. Remember this A is already success. Okay, now notice this S will try. This S will try double A. Okay, now you are basically here. It's like this. Now you are basically here. Okay, and notice now I am here because I will backtrack. Okay, I will remove this, everything is gone. Okay, now this everything is gone. Basically, now this is the situation. Okay, now this S will try double A. But the point is that only this A is matching. So on the input also we will backtrack, and basically I can say that now this is the current input symbol. Okay, is this clear? Now notice this S will try double A. Then what we will do? You can see this is the current input symbol and this is the terminal. Are they matching? Yes, they are matching. A, they are matching. So I got a small local success here. Then because this A and this A, because they are matching, so now the current input symbol is dollar. Okay, now you can see this A, is it matching the current input symbol? No, 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 no. So what it means? It means that this production also has failed. Which production? S going to A failed. Okay, then you notice one thing. To this S we will tell. Okay, to this S we will tell that all your productions have failed because S going to double A also failed. So all the productions have failed because we are applying the productions in this order. So S going to double A failed, it means all the productions have failed and you do not have any other production to try. So you have failed. Okay, now you can see, because this production has failed now. Okay, so to this s, what we will say? Tell me, to this s we will say that your ASA has failed. Yes or no? To this s we will say that, bro, your ASA production, this has failed. So what this s will tell, this initial s, what it will tell us? It will reply that no problem, if this has failed, I will try the next. Yes or no? Okay, so now this s will try the next production. Okay, so notice what will happen. Now we are in which situation? You can see, now we are in this situation that everything will backtrack. Okay, all these things will backtrack. Now basically you are here s. Okay, now basically you are here. Remember, we are here s. So on the input string, where are we? On the input string, okay, we are here, because on the input string also we will backtrack. Okay, now you are here at this s. So this initial s, it will tell us that, okay, no problem, this production has failed, I will try the next production, let me try. Now it will try the next production. Now you can see this a and a, they are matching. So on the input we will go to the next symbol, and this tick I will put because I got a small local success. Now you can see this a and this a, they are matching. So I will go to the next input symbol and I will put a tick here. I got a small local success. Now you can see from this s point of view, all its branches are successful. What it means? This s will tell us that, okay, all my branches are successful. It means I am successful, means this production has become a success. Okay, so at the end you can notice that this starting s is success. Okay, I can say that this starting s, it is successful. Starting s is successful. And also we are at dollar. Yes or no? And also we are at dollar. So what we will say? So parsing successful. So parsing successful. What it means? It means that this RDP, recursive descent parser, recognizes, accepts, recognizes double A. Okay, clear? Very simple. I hope you understood this. Very easy. Let's move on. Now let's see. What about a power 4, a power 6, a power 8? What about those? What do you think? So a power 4, I can give you as a homework. Okay, you can try a power 4. Okay, let me try a power 6. Okay, so notice some homework I am giving you. A power 4, that is a homework. Okay, a power 4, a power 8. Actually, recursive descent parser will be able to parse it. Okay, this is a homework. Try. Okay, try and see. Okay, let me give you the answer. The answer is that recursive descent parser will be able to recognize, will be able to parse a power 4, a power 8 both. Okay, is this clear? Will be able to parse. Now let's check. We will check a power 6. Okay. So the next string that we try, that is a power 6. Let's see whether recursive descent parser will be able to parse it or not. Remember, this string is generated by this grammar, but the recursive descent parser, will it be able to parse this string or not? The recursive descent parser, will it be able to recognize this string or not? That is the question. Okay, so this is our input string. Remember, any top down parser will scan the input string from left to right, one symbol at a time. So initially this is the current input symbol. Okay, now any top down parser will start from the start variable s. Okay, now notice what will happen. You can see that the question, the Ullman question, you can see this question is telling us that we need to apply, we need to try this as going to ASA first. Okay, so this production we have to try first. So remember, first we will try as going to ASA. This production we will try. Notice one thing, that this A and this A, they are matching. Very good. Okay, yes or no? So you can see this A and this A, they are basically matching. It's like this. Let me write like this. S is going to ASA. Okay, I can say this A and this A, they are matching. So on the input, I will go to the next symbol. And this is the non-terminal. So I will apply the S productions. In this order, I will apply the S productions. Okay, so here what will happen? S going to ASA. Again, you can see this A is matching with the current input symbol. So on the input, I will go to the next symbol, and you can see I have non-terminal as. Okay, so I will apply these productions in this order. I will apply. So you can see this is the non-terminal. So I will apply this A as A. Okay, very simple. Next, notice that this A is matching with this A. So on the input, I will go to the next symbol, and here I will put a tick because I got a small local success. I got. Okay, what next? You can see this is a non-terminal. So again, I will apply the production as going to A as A. Again, you can see this A is matching with the current input symbol. So I will put a small tick mark here because I got a small local success. And because this A and this A, because they are matching, so on the input, I will go to the next symbol. Okay. Next, you can see because this is the non-terminal, so the recursive descent parser will apply as productions in this order. So you can see we will apply this A as A. This is what we will apply. Okay. Notice that again this A is matching with this A, so we got a small local success. So I will put a tick mark here that we got a small local success. Okay, and you can notice that on the input I will go to the next symbol. Okay, now you can see this is the non-terminal, so I will again apply A as A. A as A. Correct? Yes or no? Notice this A is matching with this current input symbol. So I will put a tick mark because I got a small local success here. And you can see that because this A and this A, because they are matching. So on the input, I will go to the next symbol. Now we are at dollar. Okay. Now notice the next symbol that is actually S. So again, the recursive descent parser will apply A as A. Yes or no? So basically here the recursive descent parser will actually apply. Okay. Here the recursive descent parser, what it will do? Here, let me do like this. That okay, this S will go to A as A. So this S I'm putting here, this S, and this S will go to A as A. Okay, but notice one thing now. This A, this is a terminal, and this dollar, this is the current input symbol dollar. Are they matching? No, they are mismatching. Yes or no? This dollar and this A. Notice this dollar and this A. They are mismatching. So if they are mismatching, what it means? Just tell me. Simple point I'm asking. If they are mismatching, what it means? It means this production has failed. Yes or no? Because they are mismatching. So I will put a cross, small cross here. Okay, that okay, this A has failed. So I can say that this whole production S going to ASA has failed. So I will go to this S. Remember, I will go to this S and I will tell this S that your ASA production has failed. So this S will tell me that no problem, I will try the next production. Okay, yes or no? So remember, now this S will try the next production. Okay, so on the next page, let me put that this S will try the next production. So it will happen like this, that this S, okay, this S, what it will do? It will try the next production A. Clear? Remember the current input symbol, that is dollar, because already 6A they have matched. Okay, already you can see 6A are already matching. 6A are already matching. So the current input symbol, that is dollar. Okay, again you can notice that here you got A. This dollar and this A, are they matching? Again, there is a mismatch. Yes or no? Again, you can notice that this A and this dollar, again there is a mismatch. Now what? Again there is a mismatch. So now what I will do? This is me. Okay, I will tell this as that you have failed. All your productions failed. Yes or no? Okay, because this A, this itself has failed, and we are applying in this order. Basically, all the productions of this S have failed. So now basically I will say that okay, this S is a failure. Is this clear? Basically, I will say that this S, this is the S, right? Okay, this S is same as this S. So you can see this S is basically a failure. And when I say this S is a failure, then tell me. So this S is failure. What it means? It means this ASA has failed. So remember now this is me. I will basically tell this S. I will tell this as that see your ASA has failed. Yes or no? Your ASA production has failed. Agree? So to this S, I will say that bro, your ASA production has failed. So this S will tell me that okay, no problem. I will try the A production. Okay, I still have the choice available. So I will try the A production. So notice one thing that basically what will happen. we will do the backtrack. Okay, so this will be gone, this will be gone, and finally we are in this situation where we need to try the next a production. Okay, is this clear? So now what we will do, notice. Okay, so we are backtracking. Okay, you notice what I am doing, I am doing backtracking. Okay, so that's it, this everything, these things I have removed. Okay, now you can notice that what this s will do, this s will try the next production, that is a. Okay, one more thing you notice before this s will try the next production. One more thing you notice. Okay, I'm here, you know I'm here. Okay, but tell me, on the input where I am, you can notice how many a have matched? 5a. Okay, so please understand that on the input now I am here. Okay, because remember 5a are matching. You can notice 5a are matching 5a. So remember, now the current input symbol, that is this sixth a. Okay, and what this s will do, it will try a. Okay, it will try the next production. Now notice that this is also matching this a. Yes or no? This a will match the current input symbol a. So I got a small local success here, and because this a is matching with this a, so I will move to the next input symbol. But notice, this is a terminal and it is not matching. Yes or no? Notice, it is not matching here. Mismatch. Okay, because there is a mismatch, so what we need to do, I will put a cross mark here, that okay bro, you have failed. Now you can see, to this as I will say, okay, to whom? To this as I will say that you tried s going to a, that has also failed. So basically all your productions have failed. Okay, I am telling this as basically, okay, you can see, if this is me, then I am saying to this as, okay, let me use this color, that okay, to this as I am saying that you have failed, all your productions have failed. Okay, so let's put a small cross mark here, that you have failed. Now because this s has failed, so what we need to do, now we will go to the previous s. Okay, now we will go to the previous s and we will tell this previous s that, you can see, okay, because remember already this has failed, right? So to this s we will say that your asa production has failed. Okay, to this s we are saying that your asa production has failed. So this s, what it will tell us, it will tell us that okay, no problem, I will try the double a production. Okay, yes or no? So okay, so we will allow that. Okay, we will backtrack, basically we will backtrack, and you can notice that to this s, okay, to this s, now we are here. Now this s will try the next production. But notice on the input where are we, because on the input also we will backtrack. So on the input where are we, on the input you can see 4a have been consumed, 4a have been consumed, 4a we have already matched. So remember, on the input we are here, means this is the current input symbol. Okay, okay. Now this as what it will do, it will try the next production double a. Now notice, this a, is it matching the current input symbol? Yes. Okay, so small local success I got. What about this a? Remember, we will move to the next input symbol because this a and this a are matching, so we will move to the next input symbol. So now the next input symbol, or I can say the current input symbol, that is basically a. This a and this a, they are also matching, so I got a small local success I got here also, very good. Okay, but because remember this a and this a are matching, so now our next input symbol, that is dollar. Now understand something important, that from this as point of view, all its branches are successful. So this s will declare that okay, I am also successful. Yes or no? This s will declare that I am also successful. Okay, very good, no problem. Now you can see, what about, because you can see here this s is successful. Okay, already these two branches are successful. What about this a? Okay, yes or no? What about this a? So notice one thing, that this a is mismatching with this, correct? Yes or no? Notice this a and this dollar, they are mismatched. Okay, if they mismatched, then what it means, I will put a small cross mark here, that you have failed, this a has failed. Okay, what it means, it means this production as going to asa has failed. So I will tell whom, tell me, I will tell whom, I will tell this as. I am going to tell this as, to this as I will tell, notice, okay, to this as I will tell that, I will tell that, okay, as going to asa failed, your, I can say your sincerely, that your as going to asa has failed. Okay, so what this as will tell me, tell me what will be the reply of this as, what this as will reply, it will reply that no problem, I'll try next, I'll try as going to double a. Okay, is this clear? So remember, this s will try as going to double a. Okay, okay, let's allow. So you can see, you can see. Okay, let's remove everything. Basically, now this s, remember, you can see, yeah, this s. Now it will try as going to double a. Okay, this s is going to try as going to double a. Okay, but remember, before trying, on the input, where are we? On the input, because on the input also we will go backward. You can see 3a are matching, so it means that the current input symbol is now this is the current input symbol now, because you can see 3a, so far 3a has matched, 3a have matched. Okay, so the current input symbol, that is a. Okay, now this s will try double a. Okay, now you can see this a, this is matching with the current input symbol, so I will put a small tick mark, a small local success. Then this a, no, notice one thing, that this a and this a are matching, so on the input we will move to the next symbol. Now this a and this a, they are also matching, basically the current input symbol is matching with this, so a small victory I got here. Okay, local victory. And remember, on the input I will move to the next symbol. Okay, so far I can say that this s, what this s is thinking, this s is thinking that all my branches are successful, so I am also successful. Yes or no? Notice, this s is thinking that I am also successful. Okay, I am also successful, all my branches are successful, so I am also successful. Very good, no problem. Okay, now you can see that this a and the current input symbol is a, so they are matching or not, tell me. Yes, they are matching, so you can see a small victory I got here also. And because this a and this a, because they are matching, so on the input I will move to the next symbol. Okay, but notice one thing, from this as point of view, you think, from this as point of view, you think, from this as point of view, all its branches are successful. You can see, from this as point of view, just think from this as point of view, let's zoom it. This as is thinking that, okay, all my branches are successful, this is successful, this is successful, this is successful, so I am also successful. Okay, yes or no, I am also successful, so it will put a tick mark that, okay, I am also successful. Is this clear? So basically, there will be a tick mark that, okay, this s is also successful. Now what? Okay, now notice this a. Now this a, is it matching the current input symbol? No, there is a mismatch here. Okay, notice there is a mismatch here. So you can see this dollar and this a, there is a mismatch here. So because there is a mismatch, so what it means, because there is a mismatch, so this has failed. Okay, who has failed? This a has failed. So what we will tell, okay, this is me. Okay, I will tell whom, you can say I will tell this s, that bro, your s going to asa has failed. Okay, because you can see this s was going to asa and this a has failed. So basically, to this s I will say that, okay, that bro, your s going to asa production failed. Okay, so what this s will reply, this s, what it will reply, it will reply, okay, no problem, I will try s going to a. Yes or no? I will try as going to double A. Okay, no problem. Let's apply. Let's try. So let's backtrack and let's try. So remember, now this S will try. So we will backtrack. Okay, the entire thing we will backtrack, and now we will go to this S, because now this S will try double A. Okay, so the entire thing will backtrack, and now we are here. On the input, where are we? On the input also we will backtrack. On the input, where are we? Notice that on the input, actually now, on the input, actually now we are here, because only one a is matching, only one a has matched so far, so far only one a has matched. Okay, now this s will try double a. Okay, Fine. Now you can see this A and this A. Current input symbol is matching with this A. So a small local victory I got. Now you can see on the input, I will move to the next symbol. Now this A and this current input symbol are matching. I got a small local victory I got. On the input, I will move to the next symbol. Now you can see for this S point of view, all its branches are successful. So this S will say that, okay, I am also very successful. Okay, I am also successful. Now you can see that what about this A? You can see this is the current input symbol. This A is matching with this current input symbol. So this is also successful. Now this S is thinking that all my branches are successful. So this S will say that, okay, I am also successful. Okay, and notice one thing, when this A was matching, now the current input symbol is A. Okay, because you can see when this, you can notice total 4A have matched. So now the current input symbol is this. Okay, so that's it. Now you can notice that this first S is saying that I am successful. Okay, now notice the first S is saying that I am successful. The first S is saying I am successful. But we are not at dollar. We did not consume the entire input string, yes or no. So you can see the first S is saying I am successful, but we are not at dollar. We are not at dollar, yes or no. So that is the reason. What it simply means, it simply means that recursive descent parser rejects a power 6. Okay, the recursive descent parser will actually reject a power 6. I hope you understood the complete explanation. Please tell me, did you understand? So this is really a beautiful Ullman question. I hope you understood. You can notice this is the grammar. We need to apply productions in this order. Recursive descent parser with backtrack. And the question is asking that show that the recursive descent parser will recognize AA, 4A, 8A, but not 6A. Okay. So this is what we have seen. I hope you understood. Is this clear? Everything that we have seen, the complete explanation, you can see here. You can notice this is the analysis for AA. For AA, already we have seen the analysis, right? For 4A, A power 4, I gave you the homework, but actually the answer is here. So you can try. For A power 4, you try, but the answer also you can see here. For A power 6, we have seen the analysis already. The complete analysis we have already seen. For A power 8, I gave you homework, but the answer is also written here. Okay. You can try for A power 8, but answer I have given on the screen. Okay. So you can basically see this is for A power 6. Okay. This is for A power 6. How A power 6 will fail. Okay. That's it. I hope you understood. Now the next topic is how do we implement recursive descent parsing? So recursive descent parser with backtracking implementation. To implement recursive descent parser with backtracking, to implement it, what we do? For every non-terminal, we write a function. That's it. Very easy. Remember, this is how we implement recursive descent parser with backtracking. That what we do? We write a procedure, means a function. We write a function for each non-terminal. Basically, one function for each non-terminal. So in your program, in your grammar, let's assume you have 10 non-terminals. Okay, if you have 10 non-terminals, then for each non-terminal, one function we will write, one procedure we will write. Okay, so remember, very simple. This is how we implement recursive descent parser with backtracking. That in the recursive descent parsing program, that will consist a set of procedures, means a set of functions, one for each non-terminal. What it means, it means that every non-terminal is implemented as a function. Okay, the idea is very simple, that for every non-terminal we actually write a function. Okay, like this. Of course, what exactly we write in this function, okay, that will differ depending on the implementation. Okay, depending on who is writing this function. Okay, but the overall idea we will see. What we write in this function, that we will see. Okay, actually that we have already seen. Whatever the concept we have seen, the theoretical concept we have seen, we just convert it into a program. That's it. Okay, so let me tell you that in this recursive descent parser, how do we implement this recursive descent parser with backtracking? How do we implement? Very simple. That for every non-terminal, a function we write. Okay, for every non-terminal, a function we write. Is this clear? Very simple. So I hope you understood this point, that for every non-terminal, a function we write. Okay, so let me just write it here, that implementation of recursive descent parser with backtrack. Okay, so how do we implement? Very simple, that let's assume this is your grammar. In your grammar, let's assume s is the start variable. Okay, and let's assume there are some more variables. For example, let's assume there is a variable a also. Let's assume there is a variable b also. Okay, so this is your grammar. Now, so what we do in the implementation of recursive descent parser with backtracking, what we do, for every non-terminal, we write a function. Okay, for every non-terminal, we write a function. Okay, for this a also, we write a function. And for this b also, we write a function. That's it. Okay, is this clear? And tell me, which function will be the first function to call? Which function will be the first function that we will call? That is this function. Yes or no? The function corresponding to start variable. Okay, the function corresponding to start variable, this is the first function that we will call. Very simple. That's it. So very simple idea here. I hope you understood that. A recursive descent parsing program consists of a set of procedures, one for each non-terminal, means each non-terminal is implemented as a function. Okay, so you can read this here, recursive descent parsing. Recursive descent parsing, this is a form of top-down parsing that may require backtracking. And you can see it consists of a set of procedure, one for each non-terminal. One for each non-terminal. That's it. I hope you understood. Okay. And remember, how do we write these functions? You might be thinking, like in these functions, for every non-terminal, we are writing a function. But in this function, what do we write? So let me tell you, what do we write? Whatever we have seen theoretically, we just convert this into a program. That's it, nothing else. Okay, whatever we have seen theoretically, we just convert this into a program. Okay, what we have seen theoretically, you can see theoretically we have seen that how the recursive descent parser with backtracking works. Okay, how it works, we have already seen that we will begin with the start variable as, that is same as calling as. Yes or no? That is same as calling function as. So when I say we will begin with the start variable as, it is same as saying calling function as. Okay. Next, you can see what we will do. We will apply as productions one by one in a fixed order, in a pre-decided order. We will apply as productions, and you can see. Assume that this production we check. Assume that we apply this production, and assume on the input. Let's assume that the current input symbol, that is a. Now you can see there are three cases. What are the three cases? You can see, if x is a non-terminal, then what we do? I told you, if x is a non-terminal, then blindly the recursive descent parser, it will blindly apply x production without looking at the input string, without looking at the current input symbol. It will blindly apply x production. Else if x is equal to a, if x is a terminal and it is equal to a, then what we will do? Then we will move to the next input symbol, and basically we will call y. When I say go to y, what it means? When I say go to y, what it means? It simply means we are calling y. Yes or no? We will call y. Next, you can notice, else if else if x is a terminal different from a. Okay, if x is a terminal different from a, then there is a error. Okay, means it, in this situation we need to try next as production. Yes or no? Very simple. Then in this situation, this production is unsuccessful production, so we will try next as production. So remember this theory that we have already seen, a lot of questions we have already solved. Okay, you are already expert of this. Now this theory you can convert into a function, you can convert into a program, that will be the function corresponding to a non-terminal. That's it, very simple idea. Okay, on your screen I have given a typical procedure for a non-terminal. Okay, so you can see You might be thinking, for a non-terminal, how do we write a function? How do we write a procedure? So this is the procedure. You can see a typical procedure for a non-terminal in recursive descent parser. Okay, you can see in the recursive descent parser. Here you can notice we are writing the function a. Okay, we are writing the function a. You can notice what we do. What is the step number one? Forget about this code. You can see, just apply your theoretical concept that we have seen. Just apply that. You can see in this function for this non-terminal a, this is the function we are writing corresponding to non-terminal a. So in this, what will be the first thing? The first thing will be, we will choose a production. Yes or no? So you can see we will choose a production. Let's assume this is the production we are trying. Of course, the productions we will choose in a fixed order, in a pre-decided order that we have already seen. Okay, you can see here that in some order we will choose the productions. All the production we will try. All the productions should be tried in some order, in some pre-decided order. So you can see, when I write the function for non-terminal a, then what are the first step? The first step is choose a production. Let's assume this production I am choosing. Okay, very good. Now in this production also, what are the conditions? You can see the conditions are, first we will check this x1. You can see, first we will check this x1, then we will check x2, then we will check x3, then we like this. So you can see a loop is going from 1 to k. Okay, because first we will check x1, then x2, then x3, like this. Okay, so you can see this loop is going from 1 to k. What about this x1? For this x1, what you will see? You will check if it is a non-terminal. If this x1 is a non-terminal, just call it. Yes or no? If x is a non-terminal, then you call it. Okay, you call this x1. This x1 you call. Yes or no? Very simple. And remember, when you call this x1, then again what you will do? Then again the first thing is you will try x1 production. Okay, yes or no? This is the same thing I told you, that when you have s going to xyz, okay, s is going to xyz, and you can see if this x is a non-terminal, then immediately we will try x production. Okay, so you can see we will call x1. Next, you can see else if this xi is equal to the current input symbol. Okay, this x1, if this x1 is equal to the current input symbol, then what we will do? I told you, then we will move to the next input symbol. Yes or no? We will advance the input to the next symbol. Okay, and you can see otherwise, else, what it means? It means that otherwise, it means this x1 is a terminal which is different from current input symbol. In this case, there will be error. But remember, this error will not be a final error. Please understand. This error will not be a final error. This error will basically tell you that, okay, this production has failed. Try another production. Okay, is this clear? So remember, this error will not be a final error. This error will basically tell you, you can see, this error will basically tell you that, okay, this production has failed. Try another production. Okay, so you can see otherwise error has occurred. And what this error will be? This error will be that try next a production. Okay, this will be the error that you try next a production. I hope you understood. So that's it. This is how you write a function for every non-terminal. Okay, this is very easy, right? Did you notice the concept that we have seen, the theory that we have seen? We are just converting that theory into a function. For every non-terminal, for every variable, we are writing a function. And in this function, what we are doing, the same thing we are doing, which we have already seen in the concept, in the theory. Okay, that's it. So this is how we implement recursive descent parser with backtracking. Okay, this is the implementation. We create functions, or I can say we create procedures, one for each non-terminal. If you have 10 non-terminal, then 10 functions. Okay, if you have 10 variables in your grammar, then 10 functions will be created. And what will be the first function to call? Or I can say, what is your main function? The first function to call, that is your function corresponding to start variable. That is your first function to call. Okay, that's it. So you can read this. You can read this here. A recursive descent parsing program. Okay, when you implement the recursive descent parser with backtracking, then remember, the recursive descent parsing program consists of a set of procedures, one for each non-terminal. One function, one procedure for each non-terminal. And remember, the execution will begin with the procedure for the start variable. The execution will start, the execution will begin from the function corresponding to start variable. Okay, you can see, which halts and announces success. When can I say parsing will be successful? In which situation I will say that parsing is successful? Parsing will be successful if the start variable will return true. Yes or no? You can see, if the start variable will halt and announce that success, I am successful. Okay, and also we must scan the entire input string. This is also important. Basically, two things. When can I say parsing will be successful? Parsing will be successful if and only if two things should happen. The first thing is the start variable, the starting variable, the starting execution, starting of the execution, so the starting variable, if that says that okay, I am successful, and also we must consume the entire input string. In this situation, we will say that parsing is successful. Okay, very simple. And you can read this. You can see in this figure 4.13, you can notice this is figure 4.13. Okay, is this clear? Notice this is figure 4.13. Figure 4.13. So notice here we are saying, to allow backtracking, the code in this figure 4.13 needs to be modified. Basically, this code that you have, in this code, a small modification you need to do. What is that small modification? Let me tell you. The small modification is that here, where you are writing that error has occurred, here you should actually write, actually what should I write here? Where you are writing error has occurred, here you should actually write that okay, this production has failed, but you try next production. Okay, and that is what I've written here. You can see this error is not a permanent error. This is basically a local error, that okay, this production has failed, okay, try next a production. And the same thing is written here. So you can see, first we cannot choose a random production. Okay, remember, you can see in this first line, you are choosing a production. So remember, you cannot choose a random production. You have to choose productions in a specific pre-decided order. Okay, so very simple. Here you can see in the first line, you cannot choose a random production. You must try each production in some order, in some fixed order, in some pre-decided order. You can see. Okay, so you can see we must try each production, okay, in some pre-decided order. But notice one thing. Notice one thing. We will not try each production. Okay, basically, for any variable, we will try only till we get a success. For example, if this production is successful, then we will never try this production. Okay, so please understand that we will try these productions, we will try in some specific order, in some pre-decided order, we will try them. And also remember this, read this line. Failure at the line 7. This failure that you can see, this error that you see, this is not a permanent error. This is not ultimate failure. But actually, this will suggest that we need to try the next A production. Yes or no? We need to try next A production. That's it. I hope you understood. Very simple. Okay, so everything we have seen, the implementation also we have seen. You can read this recursive descent parsing with backtracking. So you can see all productions should be tried in some order, in some pre-decided order. You can see failure of some production implies that we need to try the remaining productions. Okay, or notice one thing, report an error only when there are no other rules. Okay, means when all the productions you have applied, then you report error. Okay, anyway, so that's it. So remember, we have seen the implementation of recursive descent parser with backtracking. You can see recursive descent parsing, what it does, how do we implement. You can read this. It consists of a set of procedures, one for each non-terminal. For every non-terminal, one procedure, or I can say one function we write. You can see execution begins with the procedure which corresponds to start variable. Okay, and remember when it will end. It will end if the procedure body scans the entire input string. This is this important statement. You can see we need to scan entire input string. Okay, I already told you. Next, you can see the recursive descent parser. The general recursive descent parser may require backtracking. That is, it may require repeated scans over the input. Okay, you can see if this is your input A1, A2, then you can see we will go then we will backtrack, then we will go like this. Okay, so you can backtrack. So basically, repeated scans of the input might be required. When you backtrack, then again you will scan. So that's it. Okay, you can read everything. Also remember, because this recursive descent parser, because it is a top down parser, so remember it will generate, it will produce leftmost derivation. Okay, LMD, leftmost derivation. I told you that any top down parser, whether you take LL1 parser or recursive descent parser, any top down parser will generate the leftmost derivation for the input string. Okay, that's it. Now the next topic is, when recursive descent parser does not work, in which situation we can guarantee that recursive descent parser will not work. So let's see those situations. Consider these productions. You can see S going to SA A. Notice here we have left recursion. Focus here. We have left recursion. Okay. Yes or no? We have left recursion. Now notice something interesting, that if you have left recursion in your grammar, if your grammar contains some left recursion, then what problem will happen to the recursive descent parser? To the recursive descent parser, this problem will happen. Notice one thing, because we will start from the start variable, you already know. Yes or no? The recursive descent parser will start from the start variable. Notice, let's assume that your string is A. Okay, let's assume this is your string. Remember, this grammar actually generates double A. Yes or no? If you see the grammar language, if you see LG, the language of this grammar, so you can easily notice that A plus is generated. Okay, means A, double A, triple A, 4A, basically that is generated. These strings are generated. Now notice, if this is your input string, how the recursive descent parser will work? Let's see RDP. How the recursive descent parser will work? It will start from the start variable. Any top-down parser will start from the start variable. Very good, no problem. Now notice, because this is a non-terminal, I told you, when the recursive descent parser will see a non-terminal, then blindly, without looking at the input string, without looking at the current input symbol, it will blindly apply as production. And you can see this as production, it will apply in this order. Yes or no? So basically, it will blindly apply this as production, it will apply. Okay. And now you can notice again there is a non-terminal. And I told you that in the recursive descent parser, whenever it will see a non-terminal, then without looking at the input string, without looking at the current input symbol, it will apply the as productions. Okay, so again you can notice, again as going to SA will be applied. Again you notice, again you got a non-terminal. So the recursive descent parser, what it will do? It will again apply as production. Yes or no? Again we got a non-terminal. Notice, again you got a non-terminal. The recursive descent parser, when it will see a non-terminal, then blindly, without looking at anything, without looking at the input string, without looking at the current input symbol, blindly, this recursive descent parser will apply as production. So again it will apply as A. Did you notice what is happening? Again you got a non-terminal. Is this clear? What happened here? Did you understand what happened here? Because notice there is a left recursion, so this s is basically calling s. Now when this s, basically we will just keep going, keep going, keep going, because the recursive descent parser, whenever it will see a non-terminal, then it will apply production. As production it will apply. So did you notice what happened here? Okay, basically infinite loop. Because of this left recursion, basically we fell into infinite loop. RDP, the recursive descent parser, fell into infinite loop. Is this clear? Because of fell into infinite loop, because of left recursion. Okay, is this clear? Because of left recursion, it fell into infinite loop. I hope you understood. Very simple. One more thing, actually, just I am saying, actually, can I say this infinite loop will like just keep going like this? Okay, tell me, what do you think? Can I say this infinite loop will keep going till like I can say till the end of the time? Tell me, will it happen? Will it happen that this infinite loop will keep going on till the end of time, till the end of Kali Yuga? Will it happen? No, it will not happen, because ultimately, see, we use a stake. When we implement recursive descent parser, we ultimately use a stake. Okay, so in the stake, basically, there is some stake. So that stake will overflow and we will stop. Okay, so remember one thing, this is just a small point. Okay, remember, we will say that yes, we have fell into infinite loop. That is correct. But notice, practically, from the practical point of view, theoretically we are falling in the infinite loop. Theoretically, okay, I can say theoretically the recursive descent parser has fallen into infinite loop. But practically, there is some mistake, yes or no? In the stake, initially we have s, then we have sa, then we have this, then we have this, then we have this. So ultimately, what will happen? The stake will overflow, yes or no? Okay, practically what will happen, let me write it here. Practically, the stake will overflow, and once the stake will overflow, then we can stop. Okay, practically stake will overflow, yes or no? Stake will overflow, stake will overflow, and we stop and reject. Okay, yes or no? So practically, basically, stake will overflow, but theoretically there is infinite loop. Okay, I hope you understood. Anyway, in the standard resources, in the standard book, in the standard resources, you will see this word infinite loop only. Okay, but this is just a small point, that if you notice, practically the stake will overflow, yes or no? After some time, stake will overflow. Anyway, I hope you understood this point. So we have seen that the recursive descent parser does not work when the grammar is left recursive. If your grammar is left recursive, then the recursive descent parser does not work. Okay, is this clear? Very simple. So you can see that left recursive productions, or I can say left recursive grammars, will send a recursive descent parser into infinite loop. Okay, you can read this line here, that a left recursive grammar, a left recursive grammar can cause a recursive descent parser even with backtracking. Okay, even though you already know that recursive descent parser has the backtracking facility, but still you can see the left recursive grammar will cause a recursive descent parser with backtracking to go into infinite loop. Okay, why? What is the reason? That is because when we try to expand a non-terminal a, when you try to expand this non-terminal a, then we may eventually find ourselves again and again trying to expand a. This a you will expand ab, then again this a you will expand ab, then again this a you will expand ab. So basically, again and again, you are expanding this a without consuming any input. Actually, the input is here. Notice one thing, notice one thing, when this a you are expanding ab, this a you are expanding ab, this a you are expanding ab, then actually without reading, without consuming the input, you are just keep expanding a, you just keep expanding a. Okay, so you can see that left recursive grammar can cause recursive descent parser to go into infinite loop. That's it. Okay, very simple. So this is the conclusion. Here you can see that left recursive productions will send a recursive descent parser into infinite loop. And when can I say a grammar is left recursive? In the previous lectures, we have already seen this. A grammar is left recursive if there is at least one non-terminal a, such that a can derive in one or more steps, a can derive a alpha. Yes or no? So remember, a grammar is left recursive if there is at least one non-terminal a, such that a can derive in one or more steps, a can derive a alpha. Means a is going to a alpha. This type of derivation, if it is possible for at least one non-terminal, then the grammar will be called left recursive. And you can see a left recursive grammar can cause a top-down recursive descent parser to go into infinite loop. If the grammar contains any left recursion, then recursive descent parsing does not work. Okay, very simple. So you can see, you can read here that recursive descent parser does not work when you have left recursive grammar. In your grammar, if you have left recursion, then recursive descent parser does not work. Okay, very simple. What about non-left factored grammar? If you remember, when we were discussing LL1 parser, this LL1 parser has the problem with left recursion also. Yes or no? If your grammar is left recursive, then it is not LL1. This LL1 parser also has problem with non-left factored grammar, yes or no? We have already seen this, that the LL1 parser has problem with non-left factored grammar also. If your grammar is non-left factored, then the grammar is not LL1, yes or no? So you tell me, we have already seen that recursive descent parser has problem with left recursion. The recursive descent parser will not work when you have left recursive grammar. But what about non-left factored grammar? What do you think about that? Simple question I am asking. Does recursive descent parser not work for non-left factored grammar? So let me tell you the answer, that recursive descent parser may or may not work for non-left factored grammar. Very simple question, very simple answer. Remember, the LL1 parser, please understand, the LL1 parser does not work with non-left factored grammar. If your grammar is non-left factored, then LL1 parser does not work. But if your grammar is non-left factored, then recursive descent parser may or may not work. Also notice, if your grammar is left recursive, then LL1 parser does not work. Also, the recursive descent parser does not work. Is this clear? So very simple point here. I am saying the answer is this. You can see, consider this grammar. You can notice this grammar is non-left factored because there is common prefix, yes or no? So I can say that this grammar, notice one thing, this grammar is a non-left factored. This grammar is non-left factored grammar. Okay, correct. This grammar G is non-left factored. Now you tell me, that's fine. This is non-left factored grammar, that's fine. But let me tell you that for this grammar, the recursive descent parser will work. Okay, for this grammar, the recursive descent parser actually works. Okay, so here for this G, the recursive descent parser works. There is no problem here. Okay, you can check any string you can take and you can check. For example, in this, what is LG? You can notice what is LG, that is A plus. Okay, you can take any string and you can check. For example, let me take some string. For example, let me take W equal to A. Okay, let me start with W equal to A. What the recursive descent parser will do, tell me. If I take W equal to A, then we will start from the start variable. Then we will apply this production. Then you can see this. Remember, initially, this is the current input symbol. Okay, so you can see this A and this A, they are matching. So I got a small local victory I got. Okay, so now I will move to the next symbol on the input string. Now here I got this non-terminal. So I will expand it. Yes or no? Yes. Next you can see this dollar and this A, they are not matching. So here you can see this production has failed. Because this production has failed, so what I will do? I will backtrack. Okay, remember, I will backtrack. Already this A has matched, so now we are here. Now you can see we will backtrack, and this S will try the next production. Okay. Now you can notice that this A is not matching with this dollar. So again, this has also failed. Now notice, for this S, all the productions have failed. So this S has also failed. So this production has failed. So this S will try the next production. Okay, this S will try the next production. Okay, is this clear? So you can see this is the situation. And now this S will try the next production like this. Now you can notice this A and this A, they are matching. So we will move to the next input symbol. Now you can see from this S point of view, all its branches are matching. All its branches are successful. Okay, so I can say this S is also successful. And you can see this S is successful. Also, we are at dollar. So overall, I can say that this A has been passed. Okay, this A has been passed successfully. Similarly, you can see actually that every string this RDP will be able to parse. Okay, so remember, you can actually easily check that for all W belonging to LG, RDP will be able to parse W. Okay, RDP will be able to parse W. Okay, so very simple. So remember, even though this grammar is non-left factored, Okay, because there is common prefix here, yes or no? But still, the recursive descent parser works for this grammar. Okay, but remember, I can give you another non-left factored grammar where the recursive descent parser will not work. That also I can do. Okay, so let me give you. Consider this grammar. Again, you can notice this is a non-left factored grammar. Okay, consider this grammar. This grammar G, this is also non-left factored. This is also non-left factored grammar. But let me tell you, here RDP will fail because notice here that in this order you will apply the productions. Yes or no? So now the RDP will actually fail. You take this string W equal to AA dollar. You take this string. For this string, what the RDP will do? We will start from the start variable, and I can say this is the current input symbol. We will start from the start variable. Now you can see. First, we will try this production as going to A. Now you can notice this A is matching with this A. So I got small victory here. Okay. And you can see because this A and this A are matching, so I will move to the next input symbol. And you can notice that because this has become successful, so from this S point of view, all its branches are successful. So this S will also say that I am also successful. Now notice this S is successful. This is the starting S. Yes or no? So the starting S is successful, but we are not at dollar. Yes or no? So you can notice that the starting S is successful. The starting S is successful, but we are we are not at dollar. We are not at dollar. Okay, what it simply means? It simply means that actually that this string string W equal to A not passed by RDP. Okay, is this clear? So very simple. I hope you understood this point. So basically, in this recursive descent parser, this is the same grammar as the previous. In the previous example, also the same grammar we have taken. But if you change the order of the production, then also the RDP may or may not work. Yes or no? Did you notice this interesting thing that the recursive descent parser for the same grammar it can behave in a different way if you just change the order of the production. Okay, is this clear? So if the order of production is this, then the recursive descent parser will not work for this grammar. But if you change the order of the production, then recursive descent parser is able to parse. Okay, so overall the conclusion, let me tell you. Okay, the conclusion is this, that whether you take LL1 parser or recursive descent parser, both have problem with left recursive grammar. If your grammar is left recursive, then both LL1 parser and this recursive descent parser, they will fail. Okay, but if your grammar is non-left factored, then LL1 parser will definitely fail, but RDP parser may or may not fail. Okay, very simple. So read this line here. You can notice that recursive descent parser may or may not work for non-left factored grammar, but it does not work for left recursive grammar. The recursive descent parser does not work for left recursive grammar. This is the conclusion. For all other grammar, if your grammar does not have left recursion, I can say for all the remaining grammar, means non-left recursive grammar. For all other grammar, the recursive descent parser may or may not work. So there is no specific class of grammar for which it works. Okay, one interesting thing you notice. For the LL1 parser, I can say that it will work for LL1 grammar and it will not work for other grammars. Yes or no? So basically for this LL1 parser, there is a specific class of grammar that is called LL1 grammars. Yes or no? For this LL1 parser, I can say that for this LL1 parser, there is a specific class of grammars. Let me write it here. Let's see the difference between a small point about LL1 parser and recursive descent parser. Okay, so notice that we have already seen when we were discussing LL1 parser, we have already seen that this LL1 parser, it will parse LL1 grammars. Okay, LL1 grammars. So notice that all the LL1 grammars it will be able to parse, and all the grammars which are not LL1, this LL1 parser will not be able to parse. Okay, so basically for this LL1 parser, we have a specific class of grammar which it will be able to parse, and all the remaining grammars it will not be able to parse. Okay, very simple. But remember, for this recursive descent parser, there is no such there is no such class of grammars. There is no such class of grammars. And forget about class of grammars. You can notice that for the same grammar, if you change the production order, then also the recursive descent parser will work in a different way. Yes or no? The recursive descent parser will behave in a different way if you keep the same grammar, but you just change the order of the production. Then the recursive descent parser will behave in a different way. So notice one thing, that for this recursive descent parser with backtracking, there is no such class of grammars. We do not have any specific class of grammars for which it will work and for the others it will not work. We do not have any such specific class of grammars, because notice one thing, that for the same grammar also, if you change the order of the production, then the recursive descent parser will change its behavior. That we have already seen. Okay, yes or no? So that's it. I hope you understood this point. So you can see that for all other grammars which are non-left recursive, okay, so for all the non-left recursive grammar, the recursive descent parser may or may not work. So there is no specific class of grammars for which it works, and there is no specific class of grammars for which it doesn't work. Unlike LL1, remember the LL1 parser will work for LL1 grammars and it will not work for non-LL1 grammars. Okay, so that's it. So we have seen everything here. We have seen the recursive descent parser with backtracking. We have seen the concept, implementation, a lot of practice, Ullman questions. When recursive descent parser will fail, all things, each and everything related to recursive descent parser we have seen. Okay. Let's solve these gate question in the gate exam. So far, 2 questions have come from recursive descent parser. So let's solve both these questions. Let's solve gate 1991 question. Indicate true statement. Basically, we need to find whether it is true or false. So the statement is saying recursive descent parsing cannot be used for grammar with left recursion. Is it true? Is this statement true? Recursive descent parser cannot be used for grammar with left recursion. Yes, this statement is true. Okay, remember, we have two type of top-down parser. One is LL1 parser, another is recursive descent parser with backtracking. So you can see that both of them, they will fail for left recursive grammar. If your grammar has left recursion, if your grammar is left recursive, then recursive descent parser will also fail. LL1 parser will also fail. So you can see the recursive descent parser cannot be used for grammar with left recursion. This statement is true. What is the reason? Because if you use this recursive descent parser, if you use for grammar with left recursion, then it will fall in infinite loop. Okay, that we have already seen in this lecture. Let's solve gate 2007 question. Which one of the following is a top-down parser? Recursive descent parser, yes, this is a top-down parser. The remaining, you can see LRK parser, LA LRK parser, operator precedence parser, these are actually bottom-up parser. We have already seen in the previous lectures the types of parsers, yes or no? So you can see the types of parsers that we use in the compiler design. In the compilers we use two type of parsers. One is top-down parser, another is bottom-up parser. In the top-down parser we have, one is LL1 parser, which is top-down parser without backtracking, or I can say predictive parser, and another is recursive descent parser, which is top-down parser with backtracking, or I can say top-down parser with brute force. Okay, and you can see here bottom-up parser, there are two type of bottom-up parser. One is LR parser, another is operator precedence parser. In this LR parser we have four type of parser: LR0, SLR1, LLR1, CLR1. Okay, so basically this is the types of parser. Let me tell you one more thing from the gate exam point of view. This is very important, LL1 parser. Also, these are important. Okay, these two are very important. This is not important, and this is very less important. I can say this is very less important, because so far only two questions, only two true false questions have come from recursive descent parser so far. But so this is very less important. Operator precedence parser, this is not at all important. LL1 parser we have already seen, this is very important. And this LR parser, this is bottom up parser, this is also important. So you can see, for this GATE 2007 question, which of the following is top down parser? The answer will be recursive descent parser, that is a top down parser. Okay, that's it. So that's it. We have completed our top down parser. We have seen LL1 parser, recursive descent parser, all the concepts, all the type of standard questions, all the points, important points, everything we have seen. Okay. So in this lecture, if you understood the recursive descent parser, every concept that we have seen in this lecture, all the standard questions that we have done in this lecture, if you understood, then please share your feedback. Okay. Thank you, everyone.